Our universe is an unsolved puzzle, with countless pieces still missing. For centuries, scientists have dedicated their lives to filling in the gaps, yet the picture remains elusive. We've mapped distant galaxies, detected the ripples of gravitational waves, and captured the first images of black holes. Still, these remarkable discoveries have only led us to more questions. Today, we embark on a journey through the vast expanse of everything we don't yet know about the universe. The idea of what existed before the Big Bang has captivated minds for centuries. However, this question presents one of the greatest challenges to our understanding of time and space. The Big Bang, which occurred roughly 13.8 billion years ago, marks the birth of the universe as we know it, sparking the expansion of space, time, and matter. Yet, the nature of reality before this event remains a mystery. Traditional models of physics struggle to describe a time when the universe did not exist, leaving us with only theoretical possibilities. One such theory proposes that before the Big Bang, the universe might have existed in a singular state, an infinitely dense point where the laws of physics as we know them break down entirely. Others suggest that our universe could have emerged from a prior cosmic event, or even that it may be part of an endless cycle of Big Bangs and Big Crunches. In this cyclical model, the universe undergoes repeated phases of expansion and contraction, with each big crunch followed by a new Big Bang, endlessly giving rise to new cycles of creation. An even more mind-boggling idea is the multiverse theory. It suggests that our universe might be just one among countless others, each governed by its own distinct laws of physics. Under this view, the Big Bang could simply represent one of many simultaneous events unfolding within a vast and infinite cosmos. Each universe in the multiverse may have had a different origin, leading to entirely unique configurations of matter and energy. These ideas push the boundaries of our understanding, highlighting the complexity of the cosmos and leaving us with more questions than answers. While we may not yet know what came before the Big Bang, exploring these possibilities drives the pursuit of knowledge, urging us to look beyond the edges of our universe and to question the very fabric of existence. Yet the question of why the Big Bang occurred remains just as perplexing. Though the Big Bang theory is the most widely accepted explanation for the expansion of the universe, it doesn't answer the fundamental question of what caused this monumental event. The circumstances leading up to the Big Bang remain speculative, and they continue to fuel ongoing research and debate. One popular idea proposes that quantum fluctuations in a vacuum may have triggered the Big Bang. In the realm of quantum physics, even empty space is far from empty. Fluctuations can occur, causing particles and antiparticles to appear and annihilate one another in fleeting moments. Some theorists speculate that a significant fluctuation in this quantum void could have sparked a rapid expansion, giving birth to the universe as we know it. This theory could offer insight into how the very fabric of space-time might have evolved. Another approach focuses on the idea of cosmic inflation. This theory suggests that immediately following the Big Bang, the universe underwent a brief but incredibly rapid period of exponential expansion. This process would have smoothed out irregularities in the universe, setting the stage for the cosmos we observe today. While inflation explains how the universe expanded so rapidly just after the Big Bang, it does not address the deeper question of why the Big Bang itself happened. Some cosmologists also explore the possibility of a pre-existing framework in which our universe might exist, a multiverse or some unknown cosmic structure. This perspective posits that our universe could be just one of many emerging from the interplay of physical laws far beyond our current comprehension. While these ideas remain speculative, investigating them is essential for unraveling the origins of everything we know and understanding the very nature of reality. The emergence of the laws of physics from the Big Bang is another profound chapter in the story of our universe. At the moment of the Big Bang, approximately 13.8 billion years ago, the universe was in an incredibly hot and dense state. During this early period, known as the Planck era, the fundamental forces of nature began to emerge. These forces, gravity, electromagnetism, and the strong and weak nuclear forces, are the bedrock upon which modern physics stands. As the universe expanded and cooled, the fundamental particles that make up matter began to form. Initially, the universe was a chaotic soup of quarks and gluons, the building blocks of matter. But as the temperature dropped, these particles began to combine and form more complex structures, ultimately giving rise to the matter we see today. The early universe was a hot, dense, and turbulent place, where the forces of nature were not yet fully distinct. It was a time of profound transformation, laying the foundation for the universe as we know it. However, as temperatures dropped, quarks began to combine, forming protons and neutrons, signaling the emergence of what we now recognize as the fundamental building blocks of matter. This marked the beginning of a critical phase transition, the formation of atomic nuclei during nuclear synthesis, which took place just minutes after the Big Bang. As the universe continued to cool, electrons bonded with protons, forming neutral hydrogen atoms and setting the stage for the creation of the first atoms. These atoms would eventually come together, paving the way for the formation of stars and galaxies. The laws of physics, as we understand them, arise from the symmetries and conservation principles that govern the fundamental forces and particles. Central to this understanding are the theories of quantum mechanics and relativity, which play crucial roles in determining how particles interact and how gravity shapes the universe on a cosmic scale. Yet, despite decades of progress, scientists continue their search for a unified theory, one that could seamlessly describe all the forces of nature under a single framework. This remains a focal point of research, as the quest for a grand unified theory continues to drive exploration in the field. While we have made substantial strides in understanding how the laws of physics emerged and how they govern the universe, many questions still remain unanswered. The extreme conditions of the early universe challenge our current physical theories. Events like the unification of forces and the behavior of matter and energy at such high energies require entirely new theories. Grasping these complexities not only deepens our understanding of the cosmos, but also invites us to question the very foundations upon which reality itself is built. One of the most puzzling questions in modern cosmology and particle physics revolves around the initial imbalance between matter and antimatter. According to the laws of physics, for every particle of matter, there should be an identical particle of antimatter, equal in mass but opposite in charge. Yet in the moments following the Big Bang, it is believed that equal quantities of both matter and antimatter were created. Today, however, our universe is overwhelmingly composed of matter, with only trace amounts of antimatter detectable. This imbalance remains one of the most profound mysteries in science. One possible explanation lies in a phenomenon known as baryogenesis. Baryogenesis refers to the processes that may have led to an excess of baryons, particles such as protons and neutrons, over antibaryons. Various theories suggest that conditions in the early universe could have favored the production of matter over antimatter. For example, certain interactions and decay processes might have allowed for the violation of symmetries, particularly a property called charge parity, CP, violation. This phenomenon suggests that under specific conditions, the laws of physics could behave differently for matter and antimatter. Experiments, especially those involving particle accelerators, have played a crucial role in identifying CP violation. Observations of certain decays, such as those involving particles like kaons and B mesons, show evidence of these violations, offering clues about their potential role in creating the matter-dominated universe we observe today. However, these effects alone cannot explain the vast disparity between matter and antimatter. Additional research is required to fill in the gaps and understand the true origins of this imbalance. Another avenue of exploration focuses on the theory of inflation, which proposes a rapid expansion of the universe just after the Big Bang. During this inflationary phase, any remaining antimatter could have been spread thin or pushed away from matter due to irregularities in the distribution of energy. This would have resulted in regions of the universe that were predominantly composed of matter. As we continue to probe deeper into these theories, we edge closer to unraveling the mystery of the asymmetry that defines the structure of the cosmos. Understanding the origin of this imbalance not only sheds light on the past, but also may hold the key to understanding the very nature of existence itself. The formation of the first atoms in the early universe is a truly fascinating chapter in the story of the cosmos, unfolding during an event known as recombination. Occurring around 380,000 years after the Big Bang, this pivotal moment happened when the universe had cooled sufficiently for protons and electrons to combine and form neutral hydrogen atoms. Before this era, the universe was an incredibly hot and dense plasma, a chaotic mix of quarks, gluons, protons, neutrons, and electrons, so dense that radiation couldn't travel freely through it. The frequent interactions among these particles kept the universe opaque, like a foggy haze. As the universe expanded, it gradually cooled, and when temperatures dropped to around 3000 Kelvin, electrons could finally combine with protons without being torn apart by high-energy photons. This process of recombination allowed the first stable hydrogen atoms to form, which in turn made the universe transparent to radiation for the first time. This transparency marked the release of the cosmic microwave background, CMB, a faint echo of the universe's earliest moments. But the story doesn't end with hydrogen. In the universe's infancy, a small fraction of helium was also formed during a process known as nucleosynthesis. This happened within the first few minutes after the Big Bang. During nucleosynthesis, protons fused together, creating helium nuclei, along with trace amounts of lithium and beryllium. Interestingly, most of the helium we see in the universe today was formed during this phase, rather than in later stellar processes. This marks a significant turning point in the universe's history. It was no longer a hot, dense plasma, but now light could finally travel through space. This transparency laid the groundwork for the formation of stars, galaxies, and the intricate cosmic structures we see today. Stars formed from clouds of hydrogen and helium, and through nuclear fusion, these stars created heavier elements, enriching the universe with the raw materials necessary for life as we know it. This incredible journey from a hot, chaotic plasma to a universe of stars, planets, and galaxies shows how complex and interconnected the cosmos really is. Now fast forward billions of years, and we encounter one of the greatest mysteries of modern astrophysics, dark matter. This invisible substance makes up about 27% of the total energy density of the universe. Yet despite its profound influence on the cosmos, we still have no direct way to observe it. Dark matter neither emits, absorbs, nor reflects light, making it completely undetectable by conventional means. Its existence, however, is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. One of the most promising candidates for dark matter is a class of hypothetical particles called weakly interacting massive particles, WIMPs. These particles are thought to have mass but interact only through the weak nuclear force and gravity, making them incredibly difficult to detect. Numerous experiments are underway to find evidence of WIMPs using underground detectors, particle accelerators, and other cutting-edge technologies. If WIMPs are discovered, they could provide us with a crucial glimpse into the nature of dark matter, and perhaps even unlock new realms of physics. Another possible candidate is axions, extremely lightweight particles that might also account for dark matter. Predicted by certain theories in particle physics, axions would interact minimally with ordinary matter, making them hard to detect. However, there are innovative experiments underway, such as using strong magnetic fields to convert axions into detectable photons. If successful, these experiments could reveal another key piece of the dark matter puzzle. In addition to particle candidates, some theories propose that dark matter might not be a form of matter at all, but rather a modification to our understanding of gravity itself. For example, some suggest that alterations to Einstein's general relativity could explain the phenomena we associate with dark matter. These ideas challenge our traditional concepts and open the door to a new era of physics, one that may completely reshape our understanding of the cosmos. The inability to directly observe dark matter is due to its unique properties. Unlike ordinary matter, dark matter does not interact with light or other forms of electromagnetic radiation. Our telescopes, which are designed to detect light, cannot perceive anything that does not engage with these forces. However, its gravitational influence is unmistakable. Dark matter doesn't form stars or galaxies, but instead acts as a sort of cosmic scaffold. Visible matter, like stars and galaxies, organizes itself around this invisible framework. We can observe this gravitational effect in phenomena such as the rotation curves of galaxies, where stars on the outskirts of galaxies move faster than expected based on the visible mass alone. This discrepancy suggests that an unseen mass, dark matter, is present, exerting its gravitational pull. As we continue to search for dark matter's true nature, the answers could profoundly alter our understanding of the universe and the fundamental forces that govern it. The quest to unveil the secrets of dark matter is more than just a search for a missing piece of the cosmic puzzle. It may be the key to understanding the very fabric of reality itself. In the vast and mysterious expanse of the cosmos, dark matter remains one of the most elusive and enigmatic forces that are subtly influencing the universe in ways we are only beginning to understand. One of the clearest indications of its existence comes from gravitational lensing, a phenomenon where light from distant objects is bent by the unseen mass of dark matter, revealing its presence through the curvature of space. This cosmic distortion allows scientists to map the distribution of dark matter, even though it cannot be seen directly. By observing the way light from galaxies and clusters is warped as it travels through space, researchers gain invaluable insight into the hidden gravitational influence of dark matter. Current theoretical models propose that dark matter might consist of particles that interact very weakly with regular matter, making them incredibly difficult to detect. These interactions are so faint that specialized experimental setups have yet to make definitive progress in identifying these elusive particles. Scientists are currently investigating potential candidates, including weakly interacting massive particles, WIMPs, and axions. But the precise conditions required to create or detect their faint signals demand extraordinary technology and ingenuity. The search for dark matter highlights the limitations of our current observational tools, urging the development of innovative approaches in physics. Despite these challenges, hope remains that one day we will uncover the mysteries of dark matter, piercing the veil of darkness that surrounds this substance. Its profound implications could transform our understanding of the universe, revealing the hidden forces that govern its behavior. Unlike regular matter, which interacts through electromagnetic forces to form atoms, molecules, and complex structures, dark matter interacts only through gravity. This difference in interaction means that although dark matter cannot be seen or detected through light, its gravitational influence is both significant and observable across cosmic phenomena. One of the most striking observations of dark matter's presence can be found in the rotation speeds of stars within galaxies. When astronomers measure how fast stars at the outer edges of galaxies spin, they discover that they rotate much faster than would be expected based on the visible mass alone. This discrepancy points to the existence of a vast, unseen mass, dark matter, that exerts a gravitational pull on these stars. This discovery was pivotal in understanding that dark matter constitutes a substantial portion of the total mass within galaxies, helping to hold them together. Without this unseen force, galaxies would not have the necessary gravitational support to maintain their structure. Beyond galaxies, dark matter plays a crucial role in the large-scale structure of the universe. It acts as an invisible scaffolding, creating a network of gravitational wells that guide the formation of galaxies and clusters. As matter clumps together under the influence of gravity, dark matter provides the gravitational pull needed to initiate the collapse of gas and dust, ultimately forming stars and galaxies. This interplay between dark matter and regular matter is essential in shaping the cosmic web, the vast structure that governs the distribution of galaxies across the universe. Current research is also exploring the possibility that dark matter might interact with regular matter in ways beyond gravity. Some theories suggest there could be additional, albeit extremely weak, interactions through other fundamental forces. Though these ideas have yet to be confirmed, pursuing them could dramatically alter our understanding of dark matter and the very forces that shape the universe. By investigating these potential interactions, we may unlock new insights into both dark matter itself and the fundamental principles that govern the fabric of reality. While dark matter presents a cosmic riddle, another profound mystery, the accelerating expansion of the universe, adds to the complexity of our understanding. Initially a surprising discovery, the acceleration of the universe's expansion is primarily attributed to a phenomenon known as dark energy. First observed through the study of distant supernovae in the late 1990s, the accelerating pace of expansion suggests that the universe is not merely expanding, but doing so at an ever-increasing rate. Dark energy is thought to constitute approximately 73% of the universe's total energy density, yet its exact nature remains elusive. One of the leading theories about dark energy proposes that it is a constant energy density inherent to the very fabric of space itself, an idea rooted in Einstein's equations of general relativity. Originally, Einstein included a term in his equations to account for a static universe. When it was discovered that the universe was, in fact, expanding, this term was discarded. However, the surprising discovery of accelerated expansion in the late 20th century has revived the concept of a cosmological constant, offering a potential explanation for the mysterious force driving the universe's expansion at an ever-increasing pace. The search for a deeper understanding of dark energy, like that of dark matter, continues to push the boundaries of modern physics, challenging our perceptions of the universe's fundamental nature. However, the discovery of the universe's accelerating expansion has revived interest in the idea that space itself could generate more dark energy as it stretches. This would perpetuate the acceleration of the cosmos, a cycle of growth that seems to feed on itself. Another possibility is that dark energy isn't a constant force, but rather a dynamic field, one that changes over time in response to the ever-evolving universe. This opens the door to alternative theories, such as quintessence, which proposes that dark energy's density fluctuates through different epochs of cosmic history. Quintessence models paint a more nuanced picture of the universe's expansion and suggest that dark energy might not always behave the same way. Rather, it could influence the cosmos in different ways at different stages, shaping the universe's ultimate fate in ways we are only beginning to understand. The implications of this accelerating expansion are profound, prompting us to ask fundamental questions about where the universe is headed. If dark energy continues to push the cosmos apart, it might lead to a scenario known as the Big Freeze. In this bleak future, galaxies would drift farther and farther from each other, leaving behind a cold, empty expanse. The fate of the universe hangs in the balance, and understanding dark energy is key to answering these deep questions. The quest to unravel the mysteries of dark energy remains one of the most challenging pursuits in modern cosmology. Unlocking its secrets could completely transform our understanding of the universe, how it works, how it came to be, and where it is going. The nature of dark energy, whether it remains constant or evolves over time, is still one of the most significant questions in the field. The simplest explanation of dark energy is known as the cosmological constant. This theory suggests that dark energy has a constant energy density throughout space and time, providing a steady push that drives the universe's expansion. Initially proposed by Albert Einstein in 1916 as part of his theory of general relativity, the cosmological constant was later dismissed when it was discovered that the universe was expanding. Yet, the idea was revived with the discovery that the expansion is accelerating. Under this model, dark energy doesn't change, it remains constant as the universe grows. This simplicity makes it an attractive theory, offering a straightforward explanation for the observed acceleration of cosmic expansion. As space itself stretches, the energy density of dark energy increases, leading to a continual push that accelerates the universe's expansion. However, alternative theories propose that dark energy could vary. One such theory is quintessence, which envisions dark energy as a dynamic field whose energy density shifts in response to the universe's changing conditions. In this framework, dark energy would behave differently throughout cosmic history, potentially interacting with matter and altering the expansion rate. While this complexity adds challenges to our models, it could also help explain some of the puzzling observations that the cosmological constant doesn't quite resolve. Recent data, such as galaxy clustering surveys and the study of cosmic microwave background radiation, are crucial in this search for clarity. As scientists gather more evidence and refine their models, we are one step closer to understanding whether dark energy is truly constant or if it changes with time. This knowledge would greatly enhance our understanding of the universe's evolution and its ultimate fate. Unraveling the mysteries of dark energy holds the promise of revealing fundamental insights into the very structure of the cosmos. There are several alternative theories and models that attempt to explain phenomena like galaxy rotation curves without invoking dark matter, but the compelling evidence for dark matter comes from the observation that stars at the outer regions of galaxies rotate at speeds that cannot be accounted for by visible mass alone. Various alternatives have been proposed to explain these phenomena through different mechanisms. One notable alternative is modified Newtonian dynamics, or MOND, which was proposed by physicist Mordechai Milgrom in the early 1980s. This theory modifies Newton's laws of gravity to account for the observed rotation curves of galaxies. According to MOND, at very low accelerations, such as those found at the edges of galaxies, gravity behaves differently than what Newton's laws predict. By altering the equations governing gravity, MOND can replicate the flat rotation curve seen in galaxies without requiring additional unseen mass. While MOND has had some success in certain observational cases, it struggles with broader applications, such as explaining the dynamics of galaxy clusters or the cosmic microwave background. Another alternative theory involves the concept of self-interacting dark matter. This theory still includes dark matter, but it proposes that the interactions between dark matter particles could reduce the need for large amounts of unseen mass to explain rotation curves. If dark matter particles collide with each other, this could lead to different dynamics, such as generating enough friction to alter the expected paths of stars within galaxies. Researchers are investigating whether self-interacting dark matter could bridge the gap between the need for dark matter and the observed properties of galaxies. Other theories include modified gravity models such as TVS or fifth force theories, which suggest the existence of additional forces at play. These concepts often aim to refine our understanding of how gravity operates on cosmic scales without requiring dark matter. While these alternative explanations present intriguing possibilities and are worthy of investigation, the substantial evidence supporting dark matter, including observations of gravitational lensing and cosmic structure formation, has kept it at the forefront of cosmological theories. The discourse on these alternatives continues as researchers seek to reconcile observations with the fundamental physics of the universe. When it comes to dark energy, it is believed to be uniformly distributed throughout the universe. Unlike ordinary matter, which clumps together to form stars, galaxies, and other structures, dark energy does not aggregate in the same way. Instead, it exerts a consistent but subtle influence on the fabric of space-time across vast distances. As the universe expands, the volume of space increases, and dark energy is theorized to exist as a constant energy density that fills this expanding space. This means that as new space is created through the expansion of the universe, an equivalent amount of dark energy is also added. This characteristic is one of the key reasons why dark energy is considered a compelling explanation for the accelerating expansion of the universe. Its effects become more pronounced over larger scales, suggesting a deeper role in cosmic evolution. Some models propose that dark energy might not be as constant as traditionally thought. For instance, in theories like quintessence, the energy density of dark energy can vary with time and spatial location. These models suggest that dark energy could change throughout the course of cosmic evolution, potentially leading to different behaviors in the expansion rate of the universe at various epochs. However, any such variations must still align with existing observational data, which currently supports the idea of a relatively constant distribution of dark energy. As research continues, scientists are working to refine our understanding of how dark energy behaves and its role in the future of the universe. With ongoing observations and new data, we may gain deeper insights into the subtleties of dark energy's distribution and its impact on cosmic expansion and structure formation. The search for dark matter extends beyond Earth-based experiments and into space. Satellites and space-based observatories play a crucial role in mapping the distribution of dark matter across the cosmos. By studying the gravitational effects on light from distant galaxies, scientists can create detailed maps of dark matter concentrations. These cosmic maps reveal a web-like structure, with dark matter forming the scaffolding upon which visible matter congregates. Understanding this large-scale structure is vital for comprehending how the universe evolved and how galaxies formed. The interplay between dark matter and ordinary matter in galaxy formation is a topic of intense study. Computer simulations suggest that dark matter halos form first, creating gravitational wells into which normal matter falls. This process leads to the formation of stars and galaxies within these dark matter cocoons. However, discrepancies between simulations and observations, such as the cuspy halo problem and the missing satellite problem, continue to pose significant challenges to our understanding of dark matter's role in galactic evolution. Resolving these issues is crucial, as it could shed light on the fundamental nature of dark matter and its interactions within the cosmos. Dark energy, though primarily associated with the accelerating expansion of the universe, also plays a pivotal role in shaping the growth of cosmic structures. As the universe expands more rapidly due to dark energy, gravity becomes less effective at pulling matter together. This results in a slowing or even halting of the formation of new galaxies and galaxy clusters. In the distant future, as dark energy's influence continues to dominate, the creation of new cosmic structures could cease entirely. Understanding this process is vital for predicting the universe's long-term evolution and its ultimate fate. The search to unravel the mysteries of dark energy has given rise to innovative observational techniques and ambitious projects. One of the most promising endeavors is the study of baryon acoustic oscillations, BAO. These are periodic fluctuations in the density of visible matter across the universe. By measuring these oscillations across different epochs of cosmic history, scientists can trace the evolution of the universe's expansion rate. This offers crucial insights into the properties of dark energy. New telescopes and missions are being specifically designed to study BAO and related phenomena, aiming for unprecedented precision. The potential link between dark matter and dark energy remains a tantalizing mystery in the field of astrophysics. Although treated as separate phenomena, some theories suggest a deeper connection between the two. Unified dark fluid models, for instance, propose that dark matter and dark energy might be manifestations of the same underlying substance. While speculative, these theories point toward the possibility of a profound connection between these two enigmatic forces. Exploring such possibilities could revolutionize our understanding of the universe and possibly reveal new aspects of fundamental physics. The implications of dark matter and dark energy reach far beyond cosmology and astrophysics, impacting our understanding of particle physics and the nature of space-time itself. Efforts to detect dark matter particles have driven advancements in detector technology, pushing the limits of what we know about particle interactions. Similarly, the study of dark energy challenges our understanding of vacuum energy and the fundamental properties of space. These inquiries might ultimately lead to a groundbreaking transformation in physics, bridging the gap between the vast cosmos and the minute realms of quantum mechanics. As our knowledge of dark matter and dark energy deepens, so too does our appreciation of the complexity of the universe. These mysterious components remind us that the cosmos is far stranger and more profound than we imagined. They challenge our assumptions and inspire us to explore new realms of physics and astronomy. Each new discovery in this field not only brings us closer to understanding these phenomena, but also opens doors to new questions, ensuring that the pursuit of knowledge remains dynamic and ever exciting. At the center of a black hole, often referred to as the singularity, lies a region where the gravitational pull becomes so intense that the laws of physics as we know them break down. In this extreme environment, matter is thought to collapse into an infinitely dense state, and space-time curvature becomes almost infinite. The singularity is shielded from the outside universe by the event horizon, a boundary beyond which not even light can escape. Within this core, all known physical theories, including general relativity, struggle to provide answers. General relativity predicts that gravitational forces warp spacetime, with the intensity of this warping increasing as one approaches the singularity. However, once past this point, the conventional laws governing particles and forces fail to work in ways we can measure or predict. This breakdown of physical laws presents one of the most significant challenges in modern physics, reconciling general relativity with quantum mechanics. In the case of rotating black holes, known as Kerr black holes, the singularity may not exist as a single point, but instead take on a ring-like shape. This configuration, coupled with the extreme warping of spacetime, further complicates our understanding of what occurs at the heart of such black holes. As we continue to probe these strange regions of space, our comprehension of the universe's most fundamental laws may shift, offering insights that could ultimately reshape our view of reality itself. In the vast and mysterious realms of space, black holes continue to challenge our understanding of the universe. Among the most intriguing phenomena associated with black holes is Hawking radiation, a theory proposed by physicist Stephen Hawking. This idea suggests that black holes might slowly evaporate over time, sparking a profound question: what happens to the information that falls into them? This question opens up a realm of deeper exploration, requiring a new framework of physics that merges general relativity with quantum mechanics, an endeavor now known as quantum gravity. As researchers push forward, they seek answers that could reshape not only our understanding of black holes, but the very fabric of the cosmos itself. One of the most controversial and enduring topics in theoretical physics is the nature of information inside a black hole. According to classical interpretations, once matter or information crosses the event horizon, a point beyond which nothing can escape, it's seemingly lost forever to the outside universe. This concept is referred to as information loss, and it challenges one of the foundational principles of quantum mechanics, the conservation of information. But the story doesn't end there. In the 1970s, Stephen Hawking's groundbreaking discovery of black hole radiation added a twist to the tale. He proposed that black holes could emit radiation and lose mass over time through a process now known as Hawking radiation. If this radiation caused the black hole to completely evaporate, it seemed to imply that any information about the matter that fell into it would be erased from existence. This led to what is now known as the black hole information paradox, an intellectual conundrum that pits the principles of quantum mechanics against the seemingly irreversible nature of black holes. As time passed, various theories emerged to resolve this paradox. One prominent proposal suggests that the information is not lost, but instead encoded within the Hawking radiation itself. This theory argues that while the information may be hidden within the black hole, it could eventually be released as the black hole evaporates, thus preserving the information in a highly complex form. Some researchers, like Juan Maldacena, have explored holographic principles, which propose that the information inside a black hole might actually be stored on its event horizon, a concept that further challenges our understanding of space and time. Another fascinating development in this field is the theory of black hole complementarity. This idea suggests that observers both inside and outside the event horizon of a black hole may perceive physical processes in different ways, yet these perceptions are equally valid. This concept hints at a deeper, more intricate structure of space-time, one that is still largely beyond our grasp. As our understanding of quantum gravity and string theory advances, the question of whether information is lost in a black hole remains a critical puzzle for physicists. Resolving this issue could lead to monumental shifts in our understanding of the laws that govern the universe. Supermassive black holes, those enormous, enigmatic entities at the centers of most galaxies, including our own Milky Way, pose an equally captivating mystery. These behemoths can have masses millions or even billions of times greater than that of our sun. While the process of their formation is still a subject of intense research, several theories provide insight into their origins. One widely accepted idea suggests that supermassive black holes start as smaller black holes, born from the remnants of massive stars that have collapsed under their own gravity. When a star exhausts its nuclear fuel, it can no longer counteract the immense pull of gravity, leading to a catastrophic collapse, often followed by a supernova explosion. The core that remains can form a black hole, which may then grow by merging with other black holes or accreting matter over time. Another intriguing possibility is that supermassive black holes could have formed much earlier in the universe, during the era of the first stars. At this time, vast clouds of gas might have collapsed directly into one or more black holes without forming stars first. This direct collapse could have rapidly created supermassive black holes, establishing their immense size early in the history of the cosmos. As we continue to probe the nature of black holes, both small and supermassive, we find ourselves on the cusp of discovery. Every new insight into their structure, behavior, and origins brings us closer to understanding some of the deepest and most profound questions about the universe. What we learn about these cosmic giants could ultimately change the way we see everything, from the smallest particles to the grandest galaxies. Supermassive black holes may hold the key to understanding the evolution of their host galaxies. As these cosmic giants grow, they exert an immense gravitational pull, influencing the motion of stars and gas in their vicinity. The interaction between black holes and the dynamics of galaxies creates a fascinating and complex relationship that continues to shape our view of the universe's structure and development. With advancements in observational technology, scientists are uncovering more about these enigmatic entities and the pathways that led to their formation. The event horizon of a black hole is often described as the ultimate boundary, a point beyond which nothing can escape, not even light. This makes it one of the most mysterious regions in our understanding of the cosmos. Yet, what lies beyond this boundary remains one of the greatest scientific mysteries. Once an object crosses the event horizon, it is believed to be drawn inexorably toward the singularity, the point at the center of the black hole where gravity compresses matter to infinite density. Here, the laws of physics as we know them begin to break down, and space-time is thought to curve infinitely. This creates a challenge for physicists trying to reconcile the theories of general relativity with the principles of quantum mechanics. The singularity raises many intriguing questions. For instance, how does time behave in such an extreme gravitational environment? While time in the outside universe moves forward normally, for an observer crossing the event horizon, time would appear to flow normally until they approach the singularity, where both time and space lose their conventional meanings. Some theories suggest that inside a black hole, alternative realities or even parallel universes could exist, fueling much speculation and debate within the scientific community. At present, black hole models don't provide concrete answers about what happens beyond the event horizon, but ongoing research continues to advance, possibly bringing us closer to unraveling the mysteries hidden within these cosmic enigmas. One particularly fascinating area of study is the potential for harnessing energy from rotating black holes, known as Kerr black holes. These black holes not only possess mass, but also angular momentum due to their rotation, which opens up intriguing possibilities for extracting energy from their dynamics. One proposed method for energy extraction is the Penrose process, named after physicist Roger Penrose. In this theory, an object can be sent into the black hole's ergosphere, a region just outside the event horizon where space-time is dragged along by the black hole's rotation. Inside this region, an object can be split into two parts. One part falls into the black hole, while the other escapes with more energy than the original object. In theory, this process could allow us to extract rotational energy from the black hole, though its practical application remains firmly in the realm of theoretical physics. Another fascinating concept is Hawking radiation, proposed by physicist Stephen Hawking. This theory suggests that black holes could emit radiation due to quantum effects near their event horizons. While the radiation emitted by large black holes is incredibly small and difficult to detect, the idea raises the possibility that black holes might gradually lose mass over astronomical timescales, potentially offering a source of energy in the distant future. While these concepts are compelling from a theoretical standpoint, practical applications of harnessing energy from black holes are still far beyond our current technological capabilities. However, exploring these ideas deepens our understanding of extreme physics and sparks imagination about potential future energy sources in advanced civilizations. Binary black hole systems, where two black holes are gravitationally bound to each other, provide another fascinating glimpse into the dynamics of gravitational interactions. As they orbit each other, they gradually lose energy in the form of gravitational waves. ripples in spacetime caused by the accelerating masses of the black holes. This emission of gravitational waves causes the black holes to slowly spiral inward toward each other. Initially, this process takes millions or even billions of years. However, as the black holes get closer, the rate at which they spiral inward accelerates. Eventually, they enter a phase known as the merger, during which a dramatic burst of gravitational waves is released. These waves can be detected by instruments like LIGO and Virgo, providing scientists with valuable data about the behavior of these mysterious systems. The merger event itself results in the transformation of two separate black holes into a single, more massive black hole, marking a crucial moment in the life cycle of these cosmic entities. During the final moments of a black hole's existence, a colossal release of energy occurs, the intensity of which depends on the initial spins and masses of the black holes involved in the merger. The resulting black hole's characteristics are shaped by these early factors, and the aftermath plays a crucial role in the growth of supermassive black holes at the centers of galaxies. This, in turn, offers vital clues for understanding galaxy evolution. But there's more to these binary black hole systems. They are essential for deepening our comprehension of gravity's true nature and the very fabric of space-time. As technology continues to advance, particularly with the detection of gravitational waves, our grasp of binary black hole evolution becomes more nuanced, revealing the complexities of some of the universe's most powerful phenomena. When it comes to the end of a black hole's life, one of the most perplexing and thought-provoking events is its evaporation, a process predicted by the theory of Hawking radiation. Over vast stretches of time, black holes lose mass by emitting particles due to quantum effects near their event horizons. These effects arise from virtual particles, pairs that constantly pop in and out of existence in the vacuum of space. As a black hole slowly evaporates, its mass gradually declines. However, something extraordinary happens in its final moments. The rate of Hawking radiation emissions increases exponentially, causing a rapid loss of mass. As the black hole shrinks, it becomes hotter and the radiation emitted becomes more intense. This phase is often visualized as a cosmic explosion, an energy release of unprecedented scale. In these last moments, the black hole may emit bursts of high-energy particles, including photons and other fundamental particles, releasing vast amounts of energy into space. This powerful outpouring of energy, if it occurs within a stellar environment, could offer profound insights into how stellar remnants interact with their surroundings during such a transformative phase. But there's an even deeper mystery: the information paradox. In these final moments, a crucial question arises. Does the information about the matter that fell into the black hole get destroyed forever, or is it somehow preserved, accessible after the black hole evaporates? This paradox remains an open problem in theoretical physics, sparking fierce debate and driving investigations into the very nature of information in our universe. As scientists continue to study black holes and their evaporation, we move closer to unlocking the mysteries of quantum mechanics and understanding the true nature of space-time itself. One of the most profound questions in cosmology is the true shape of the universe. This question is closely tied to the underlying geometry of space-time, and our current understanding suggests that the universe can be described using various geometrical models, depending on its average matter and energy density. One possibility is a flat universe, akin to a sheet of paper. In this model, parallel lines would never meet, and geometric rules would follow the familiar principles of Euclidean geometry. Observations, especially those of the cosmic microwave background radiation, suggest that the universe is very close to flat on a cosmic scale. This implies that the total density of matter and energy is nearly equal to the critical density required for this flat geometry. Another scenario proposes a closed universe, similar to the surface of a sphere. In this model, the universe is finite but unbounded. If you were to travel in a straight line, you would eventually return to your starting point. The curvature of space in this model leads to different geometric rules, resulting in phenomena such as the potential for a big crunch, where the universe might eventually collapse back into itself. An open universe unfolds like a saddle, where parallel lines gradually begin to diverge, suggesting that the universe could expand forever, never returning to a previous state. Each model of the universe brings with it distinct implications about the fate of everything within it: light, matter, and space itself. The classical models of cosmic shape are continually being reevaluated, particularly with the influence of dark energy, a mysterious force that accelerates the expansion of the universe. Understanding the true shape of our cosmos is a puzzle that remains unsolved, with ongoing observations and studies steadily refining our understanding. As we probe deeper into the universe, astronomers are piecing together a breathtaking picture of cosmic structure and destiny. Indeed, the universe harbors colossal formations that surpass the scale of individual galaxies. Superclusters of galaxies are themselves vast collections bound together by gravity. One of the most extraordinary discoveries is the existence of cosmic filaments, which form a vast interconnected web of galaxies and dark matter, stretching across hundreds of millions of light years. The largest of these filaments are often called superclusters of superclusters. For example, the Laniakea supercluster, which contains our own Milky Way, is just one part of an even more extensive web of galaxy clusters and filaments. These galactic superstructures don't just appear randomly. The complex interplay of gravity shapes them, and their distribution hints at the deeper, unseen forces governing the cosmos. Beyond these grand structures, we encounter enormous voids, regions of space where galaxies are sparse or non-existent. These vast voids, stretching for hundreds of millions of light years, are some of the largest empty spaces in the universe, and their existence provides critical insight into the large-scale organization of the cosmos. The intricate balance of densely packed regions filled with galaxy clusters and vast, empty voids forms the architecture of the universe. As astronomical technologies advance, scientists continue to explore these enormous structures, shedding light on the forces at play over cosmic scales. This hierarchical structure, ranging from galaxies to superclusters and beyond, reveals how gravity and dark matter have influenced the universe's evolution over billions of years. Each new discovery brings us closer to understanding how the universe's fabric was woven and how it continues to evolve, shaping the intricate web we observe today. The formation of the first galaxies was a pivotal moment in cosmic history, occurring after the Big Bang, when the universe was still cooling and expanding. In the early universe, matter was mostly uniform, composed of hydrogen and helium gas, but subtle density fluctuations caused by gravitational instability disrupted this uniformity. Tiny variations in matter attracted more gas, and over time, these areas collapsed under their own gravity, forming the first star clusters. These primordial stars were massive and short-lived, burning brightly before exploding as supernovae. The aftermath of these explosions seeded the surrounding gas with heavier elements, setting the stage for the formation of the next generation of stars and galaxies. This process of galaxy formation wasn't uniform. Some regions experienced rapid star formation, leading to the creation of smaller galaxies that merged over time. Through this cosmic dance of mergers, larger and more complex galactic structures emerged. The role of dark matter in this process cannot be overstated. It provided the invisible scaffolding that allowed these galaxies to form and cluster together. Without dark matter's gravitational influence, the universe would look very different. As galaxies continued to evolve, they established the framework for the structures we observe today, influencing the formation of the cosmic web. The filamentary structure of the cosmic web is a direct consequence of gravity. It arises from gravitational interactions on an immense scale, shaping how galaxies, galaxy clusters, and dark matter are distributed throughout the universe. In the early universe, matter was evenly spread, but tiny quantum fluctuations from the inflationary period created slight variations in density. Over time, gravity intensified these fluctuations, causing regions of higher density to collapse into galaxies and clusters, while less dense regions expanded. This uneven distribution eventually gave rise to the vast network of filaments and nodes that make up the cosmic web. These filaments are primarily made of dark matter, a mysterious substance that doesn't emit light, making it invisible to traditional telescopes. Yet dark matter exerts a powerful gravitational pull, influencing the movement of visible matter, including galaxies and clusters. Galaxies tend to move toward these filamentary structures, acting like cosmic highways, drawing galaxies together through gravitational attraction. This creates a stark contrast with the vast voids that lie between the filaments, regions where galaxies are few and far between. The vast, empty voids in the universe are critical to understanding its large-scale structure. These voids form due to the complex interplay of gravity and dark matter. Early in the universe's history, matter was relatively uniformly distributed, influenced by quantum fluctuations. As the universe expanded and cooled, gravity began to shape the distribution of matter, pulling it into dense regions where galaxies and clusters formed. Voids represent the less dense areas where matter was insufficient to form galaxies. Their study is crucial to understanding the origins of cosmic structure and how the universe evolved to its current state. The cosmic web, an intricate network of galaxies, clusters, filaments, and voids, is a testament to the power of gravity and dark matter in shaping the universe over billions of years. As we continue to observe and study these vast structures, we uncover more about the forces that shape them, revealing the complex and dynamic nature of our universe. However, in regions where the density of matter was lower, the gravitational pull was not strong enough to attract significant amounts of material. As a result, vast stretches of space remained largely empty. These voids, as we now call them, are the vast expanses between galaxies that we observe today. Over time, as galaxies began to form and evolve, their interactions fueled the expansion of these voids. The gravitational pull between clusters and filaments of galaxies caused space itself to stretch, drawing galaxies toward areas devoid of matter. This left the emptier regions even more desolate. The effect created what we now recognize as the cosmic web, an intricate structure where clusters and filaments of galaxies define the boundaries of enormous voids. These voids can stretch across hundreds of millions of light years, occupying vast spaces in the cosmos. Studying them is crucial for understanding the very architecture of the universe. They provide a unique opportunity to explore how dark matter, dark energy, and ordinary matter interact, offering vital clues about the universe's overall dynamics and its evolution. The presence of voids serves as a testament to how gravity has acted differently across the universe, shaping the cosmic structure we observe today. The evolution of galaxy clusters is a continuous process that unfolds over billions of years. These clusters are shaped by the gravitational interactions between galaxies within them, as well as their relationship with the surrounding matter and dark energy. Galaxy clusters form through the merging of smaller groups of galaxies, which themselves are made up of stars, gas, and dark matter. Initially, galaxies begin to draw closer to one another under the influence of gravity. This leads to the formation of a cluster, which can contain many galaxies, some of which are already engaged in interactions with each other. As time passes, these galaxies continue to merge, triggering bursts of star formation and altering their appearance. The gravitational forces within the cluster bind the galaxies together, facilitating a complex interplay of movements and interactions. Over time, the cluster acquires new members, drawing in nearby galaxies and matter through its gravitational pull. The movement of hot gas, known as the intracluster medium, fills the space between galaxies. This gas, which can emit X-rays, provides crucial data about the cluster's mass and temperature. The intracluster medium plays a vital role in the cluster's evolution. It can cool and condense, forming new stars within galaxies, or it can be heated, further influencing the overall dynamics of the cluster. As galaxy clusters age, they undergo significant changes. One of the most striking phenomena is cluster merging, where two or more clusters collide, leading to complex interactions that can reshape their structures. As these clusters grow and evolve, they become more massive and may form hierarchies within the larger cosmic structure. Understanding the evolution of galaxy clusters is essential, as they serve as natural laboratories for studying the effects of dark matter, dark energy, and the fundamental laws that govern cosmic evolution. This helps us gain insight into the origins and future of the universe itself. The search to determine how common Earth-like planets are in the universe has gained significant momentum in recent years. Advancements in observational technology and space missions, such as the Kepler Space Telescope, have provided crucial data. Estimates suggest that Earth-like planets, defined by their similar size, composition, and distance from their stars, could be surprisingly common throughout the cosmos. Research has shown that potentially habitable planets are often found within what is known as the habitable zone of their stars. This is the region where conditions might allow liquid water to exist on a planet's surface, a key ingredient for life as we know it. Studies indicate that many stars host multiple planets, and a significant portion of those planets reside within their star's habitable zone. Some estimates propose that as many as 1 in 5 stars could have an Earth-sized planet within the habitable zone. This discovery opens up exciting possibilities about the existence of life beyond our planet. Binaries can significantly influence the types of planets that form in a system. For instance, gas giants and icy bodies might form at different distances from their stars than they would in a solitary star system. The gravitational influence of both stars in a binary system can even lead to the capture of planets that form farther out, or remnants of disrupted bodies. This broadens the diversity of planetary types that could exist. Furthermore, the orbits of planets in binary systems are often more complex. Some planets might maintain stable orbits, much like those found in single-star systems, while others could experience more eccentric or unstable paths due to the gravitational tug-of-war between the two stars. This variation creates a wide array of potential planetary systems, offering a more extensive field for exploration into the conditions under which planets form. A key area of inquiry in this field is understanding the potential for life elsewhere in the universe. One crucial aspect is determining the upper size limit for a habitable planet. Scientists must assess a range of factors that influence the conditions necessary for life as we know it. Typically, habitable planets fall within a specific range, known as the habitable zone, where liquid water can exist on the surface. These planets are often referred to as Earth-like worlds. However, as a planet grows in size, several factors come into play that can impact its habitability. One primary consideration is gravity. Larger planets tend to have stronger gravitational fields, which can retain thicker atmospheres composed of gases that help insulate the planet and maintain surface pressure. While a substantial atmosphere is crucial for sustaining life, there is a limit to how large a planet can get, while still maintaining habitable conditions. Planets that become too large, often classified as super-Earths, could have atmospheres dominated by gases like hydrogen and helium, ultimately becoming gas giants. This transition would likely eliminate the possibility of land and liquid water on the surface, conditions vital for life as we know it. Geological activity also plays a significant role in a planet's ability to support life. Larger terrestrial planets tend to have more internal heat, which can drive geological processes such as plate tectonics and volcanic activity. These processes can create diverse climates and ecosystems. However, excessive geological activity can also result in extreme conditions, such as high pressures and temperatures, which might render a planet inhospitable. This balance of factors suggests that while planets up to 2 or 3 times the size of Earth may still maintain habitable conditions, the likelihood of retaining Earth-like environments decreases as a planet grows larger. As research advances and more exoplanets are discovered, our understanding of habitability will continue to evolve, possibly revealing surprising limits on the potential for life in the universe. Then there's the potential for life to exist in forms far beyond our imagination. The diversity of possible alien biochemistries is staggering. On Earth, life is primarily carbon-based, utilizing water as a solvent and relying on amino acids, nucleic acids, and lipids to create the complex structures of biological organisms. However, in the vastness of the cosmos, life could take on forms entirely different from anything we know, perhaps using alternative elements or solvents, leading to a rich and diverse tapestry of life that may exist beyond the familiar. However, when we venture beyond our planet, our imaginations are set ablaze with the possibilities of life forms that might thrive under entirely different conditions. Scientists, for instance, have speculated about the potential for silicon-based life. Silicon shares many of the chemical properties of carbon, meaning it could theoretically form the backbone of complex molecules. Life based on silicon might inhabit environments that are scorching hot, like those near volcanic activity, or even on planets and moons in our own solar system that harbor extreme conditions. But beyond just the molecular structure of life, the very conditions necessary for survival could lead to an incredible variety of biochemical processes. Take Earth's life forms, for example. They depend on oxygen to power cellular respiration. Yet, alien organisms could use entirely different elements such as sulfur or methane to fuel their energy-producing pathways. This could allow life to exist in places that were once thought to be inhospitable, like the thick, toxic clouds of Venus or the icy surfaces of Europa and Enceladus, where hidden oceans might harbor life forms that remain unseen. Moreover, the genetic systems of extraterrestrial organisms might not mirror our own in any way. They could utilize alternative nucleic acids instead of familiar DNA and RNA, or even adopt entirely new methods of information storage and transfer. Exploring these possibilities challenges everything we think we know about biology, expanding the limits of what life could be and forcing us to rethink its forms across the universe. One particularly intriguing possibility lies in methane-based ecosystems and environments that would foster life vastly different from anything on Earth. A prime candidate for such an ecosystem is Titan, Saturn's largest moon, where methane and ethane exist as liquids, creating vast lakes and rivers. Life on Titan would need to adapt to the moon's frigid temperatures, which hover around -180 degrees Celsius. Organisms here could utilize methane rather than oxygen as their primary energy source. Instead of relying on photosynthesis like terrestrial life, Titan-based organisms might engage in chemosynthesis, creating energy through chemical reactions involving methane and hydrogen. These hypothetical life forms would likely possess biochemistries uniquely suited to their environment. Their cell structures might evolve to withstand the low temperatures and high viscosity of liquid methane. Think of Earth's extremophiles, organisms that thrive in extreme conditions like hot springs or deep ocean vents. Similarly, Titan's life forms might develop specialized membranes or rigid bodies capable of surviving in methane's harsh environment. Their appearance would be unrecognizable by Earth standards, perhaps transparent with pigmentation adapted to the dim light of distant stars, or even solid crystalline formations capable of absorbing and utilizing available energy sources. Metabolism in such organisms would likely follow entirely new biochemical pathways, leading to cellular structures that differ fundamentally from anything we've observed on Earth. The absence of water as a solvent means life wouldn't depend on amino acids in the same way. Instead, alternative molecules could play crucial roles in both the structure and function of life, opening a window into biological forms beyond our wildest imagination. One of the most exciting frontiers of modern astronomy is the search for biosignatures on distant exoplanets. Researchers are focused on identifying chemical markers in the atmospheres of exoplanets that could suggest the presence of life. These biosignatures often involve gases typically produced by biological processes. For example, the simultaneous presence of oxygen and methane in an exoplanet's atmosphere could indicate biological activity, as these gases tend to react with each other and would need a constant source of replenishment, something life itself could provide. One of the most powerful tools available for detecting these biosignatures is the transit method. This involves observing the light from a star as a planet passes in front of it. During this transit, a small amount of the star's light filters through the planet's atmosphere, allowing scientists to analyze the spectrum of light that emerges. This spectral data reveals the chemical composition of the atmosphere. By identifying specific absorption lines, researchers can determine whether certain biosignature gases are present, potentially confirming the existence of life on distant worlds. In the future, space missions will leverage advanced space telescopes equipped with cutting-edge spectrographs to observe smaller and cooler exoplanets within their stars' habitable zones. The James Webb Space Telescope, for instance, is expected to revolutionize our ability to study exoplanet atmospheres and identify potential biosignatures. These instruments will allow scientists to search for gases like oxygen, ozone, methane, carbon dioxide, and others. When these gases are found together, they could indicate biological processes at work. However, as we search for biosignatures, it's crucial to stay cautious of false positives. Some chemicals can emerge from abiotic processes or geological phenomena. Therefore, scientists must carefully analyze every discovery, considering all available evidence and alternative explanations. This rigorous examination will bring us closer to understanding whether life exists elsewhere in the universe and provide deeper insights into what life beyond Earth might look like. A supernova occurs when a star ends its life with a violent and dramatic explosion. This explosive event can be triggered by two different processes, depending on the star's mass. First, consider massive stars, those with at least 8 times the mass of our Sun. As these stars burn through their nuclear fuel, their cores grow heavier and denser, leading to a gravitational collapse. When fusion reactions that normally counteract gravity can no longer sustain the core, temperatures and pressures soar to levels so extreme that they initiate a series of reactions that create iron. Once iron accumulates in the core, the star can no longer generate energy through fusion, causing it to collapse under its own gravity. This collapse happens in mere seconds, triggering a rebound effect that ejects the star's outer layers. The shockwave from this catastrophic event releases roughly 100 times more energy than the Sun will emit over its entire lifetime. This type of supernova is classified as a Type II supernova. The second major cause of supernova, known as a Type IIa supernova, occurs in binary star systems where a white dwarf resides next to a companion star. The white dwarf can accumulate material from its partner, causing its mass to approach a critical limit called the Chandrasekhar limit. Once the white dwarf exceeds this limit, it triggers a runaway nuclear fusion reaction in a cataclysmic explosion, destroying the star completely. This explosion is characterized by its immense brightness and the absence of a neutron star or black hole, unlike the Type II scenario. Both types of supernovae play a vital role in the universe. They are responsible for dispersing heavy elements, enriching the cosmos, and contributing to the formation of new stars, planets, and the building blocks of life. Moreover, the energy released in a supernova can significantly influence surrounding environments, impacting nearby star formation and potentially even altering the dynamics of entire galaxies. Magnetars, some of the most fascinating objects in the cosmos, generate magnetic fields stronger than those of ordinary neutron stars, often exceeding 1,000 times their strength. To understand how this happens, it's important to examine the life cycle of massive stars. Once such a star exhausts its nuclear fuel, it undergoes a supernova explosion, leaving behind a dense core that collapses into a neutron star. What makes magnetars unique is the combination of conditions during their formation and the processes that occur later in their lives. The intense magnetic fields of magnetars arise primarily from their rapid rotation and the extreme densities within them. As the core collapses, it spins faster due to the conservation of angular momentum. This rapid rotation, coupled with the complex motions of electrically charged plasma inside the star, generates powerful magnetic fields through a process known as the dynamo effect. The movement of charged particles within the hot, dense interior of the magnetar amplifies the magnetic field to incredible strengths, producing one of the most fascinating and mysterious phenomena in the universe. The material within a neutron star consists of neutrons, protons, and other subatomic particles, all packed into an incredibly small volume, creating a state of matter unlike anything found on Earth. This extreme density gives rise to extraordinary conditions capable of distorting magnetic fields in ways that are simply mind-boggling. As the star evolves, processes like convective motions and the interaction of magnetic fields contribute to the strengthening and complex structuring of its own magnetic field. The result is a large-scale, highly organized magnetic field that stands apart from anything typically observed in other celestial bodies. In a surprising twist, magnetars, highly magnetized neutron stars, are also prone to magnetic outbursts. These bursts release staggering amounts of energy, primarily in the form of X-rays and gamma rays. Such flares occur when the star's magnetic field undergoes a reconfiguration, often caused by internal stresses that destabilize the field. This delicate balance of intense magnetic forces, combined with the dynamic internal processes of these stars, makes magnetars one of the most fascinating and enigmatic objects in the cosmos. Their strange behavior continues to inspire researchers, driving ongoing investigations into their extreme and mysterious physics. Fast radio bursts, FRBs, are one of the most puzzling phenomena in the field of astrophysics. These fleeting, high-energy bursts of radio waves last only a few milliseconds, but their origins remain shrouded in mystery. Several theories have emerged, with the leading hypothesis suggesting a connection to catastrophic events in the cosmos. Some scientists believe that FRBs might be linked to the collapse of massive stars, leading to the creation of neutron stars. In particular, magnetars with their extraordinarily strong magnetic fields might be responsible for some of these bursts. When the magnetic fields of magnetars undergo sudden reconfigurations, or when energy is released from these fields, the resulting radio waves could be the cause of the FRBs that we detect on Earth. There are also other intriguing possibilities, including the idea that these bursts may be signals from exotic and distant objects, such as black holes or the mergers of compact objects like neutron stars. When two neutron stars collide, the resulting cataclysmic event may create the extreme conditions required to produce such rapid bursts of energy. Speculations even exist about the potential for extraterrestrial civilizations sending signals, though this hypothesis remains speculative and far less favored than the astrophysical theories. Despite the progress in understanding these bursts, pinpointing their exact sources remains a formidable challenge. Many FRBs are repeated, which adds complexity to their nature and tracking. By studying the dispersion of these radio signals, scientists can infer the distance and environment from which they originate, providing valuable new insights into their cosmic origins. As research continues and technology advances, the mysteries surrounding fast radio bursts are gradually being unraveled, offering tantalizing glimpses into the extreme astrophysical processes at work across the universe. Star formation in extreme environments, such as the chaotic centers of galaxies, presents a unique and fascinating challenge. In these regions, especially around active supermassive black holes, the conditions are unlike anywhere else in the cosmos. Intense radiation levels, extreme gravitational forces, and violent turbulence all play a part in shaping the environment. Yet, despite these inhospitable conditions, stars continue to form, albeit through mechanisms that differ greatly from those found in quieter regions of space. A critical factor in star formation within these galactic centers is the presence of vast amounts of gas and dust, which gather into dense molecular clouds. These clouds are often subjected to the chaotic forces of the supermassive black hole at the galaxy's core, as well as the intense radiation generated by the surrounding energetic activity. Remarkably, while the intense radiation could easily disrupt star formation, it also serves to compress the gas, aiding in the very process of star creation. As these gas clouds become increasingly dense, they can collapse under their own gravity, eventually giving birth to new stars. Even though the radiation from the supermassive black hole's accretion disk heats and ionizes much of the surrounding gas, certain regions of the molecular clouds manage to shield themselves from this external heat. This cooling effect allows portions of the clouds to remain at lower temperatures, thus preserving the conditions necessary for star formation to continue. The contrast between the destructive and constructive forces in these environments makes star formation in the centers of galaxies one of the most captivating and perplexing phenomena in the universe. And so the interactions between gas clouds and the universe are not just mere collisions. They can trigger shock waves that compress material further and spark the formation of new stars. In environments so extreme, star formation may occur at an accelerated pace, creating massive stars that evolve rapidly. These stars, burning brightly with their intense energy, may reach the end of their lives in spectacular supernova explosions. These cataclysmic events enrich the surrounding regions with heavier elements, laying the foundation for even more stars to form. This cyclical process of birth and destruction is a driving force behind the dynamic evolution of galaxies, illustrating that even in the most hostile conditions, the universe exhibits an incredible ability to nurture and create new stars. Ultra-high energy cosmic rays, some of the most mysterious and energetic particles in the cosmos, present another fascinating chapter in this tale. Their energies soar beyond 1 billion giga-electron volts, far surpassing those produced by even the most powerful human-made particle accelerators. For decades, scientists have been puzzled by the origin of these particles. with their sources primarily linked to the most energetic astrophysical phenomena known to us. One leading candidate for the origin of ultra-high energy cosmic rays lies in supernova remnants. When massive stars reach the end of their lives and explode in a brilliant supernova, they release an enormous amount of energy, creating shock waves that can accelerate particles to incredibly high energies. These shock waves interact with the surrounding gas and magnetic fields, providing the right conditions for particles, primarily protons, to gain energy and escape the remnants of the explosion. While this mechanism offers a plausible explanation, it does not fully account for all of the highest energy cosmic rays detected across the universe. Another compelling contender is the active galactic nuclei, particularly those found at the centers of galaxies where supermassive black holes reside. As matter spirals into these black holes, immense amounts of energy are released, often in the form of powerful jets. These jets can accelerate particles to ultra-high energies with the surrounding environment, characterized by turbulent magnetic fields and extreme gravitational forces, creating an ideal setup for cosmic ray acceleration. Additionally, gamma-ray bursts, extremely energetic explosions linked to the collapse of massive stars or the mergers of compact objects, have also been proposed as potential sources of ultra-high energy cosmic rays. The energy unleashed during these events is so vast that it can accelerate particles to incredible velocities, pushing them to the highest energies known. Through these various mechanisms, the universe not only presents us with spectacular phenomena, but also constantly reshapes the cosmos, creating conditions that can propel particles to unimaginable extremes. Each discovery about these cosmic rays brings us one step closer to understanding the violent but dynamic processes that govern the universe's evolution. However, despite significant progress in observational techniques, determining the exact mechanisms and locations of particle acceleration in extreme cosmic environments remains a key challenge in astrophysics. The origins of ultra-high energy cosmic rays, particles that travel across the vastness of space at nearly the speed of light, remain elusive. Researchers worldwide are conducting groundbreaking studies using state-of-the-art observatories in an attempt to establish direct connections between these detected cosmic rays and their potential sources. The goal is to unravel the mysteries surrounding these energetic particles and gain a deeper understanding of some of the most powerful phenomena in the universe. Binary star systems offer an intriguing example of cosmic cooperation and conflict. These systems consist of two stars orbiting a common center of mass, where each star's fate is intertwined with its companion. The exchange of mass between the stars, a process that significantly shapes their evolution, is a key area of study. As one star evolves and exhausts its nuclear fuel, it often expands into a more volatile state, often becoming a red giant. This expansion can lead to a variety of outcomes, depending on the specific dynamics of the binary system. When one star in a binary system expands, its outer layers may spill over into the gravitational pull of its companion. This mass transfer is often facilitated by the formation of an accretion disk around the receiving star. This disk acts like a funnel, drawing material from the donor star and spiraling it downward to the surface of the companion. The efficiency of this mass transfer depends on a variety of factors, such as the distance between the stars and how rapidly the donor star expands. Mass transfer in these systems can be categorized into two main types: stable and unstable. In stable mass transfer, material is transferred gradually and steadily, allowing the receiving star to adjust over time. This process can lead to long-term changes in the star's brightness and composition. In contrast, unstable mass transfer can result in rapid, catastrophic exchanges, often leading to explosive events like nova eruptions. During these outbursts, the material that has been accreted undergoes thermonuclear reactions, releasing vast amounts of energy. These eruptions can be seen as the explosive culmination of a star's evolution. The impact of mass transfer can drastically alter the life cycles of both stars in a binary system. For example, the receiving star may accumulate enough mass to become a white dwarf, a neutron star, or even a black hole, depending on the amount of material it takes in and its initial mass. This dynamic interplay of mass exchange shapes not only the star's fates, but also produces some of the most spectacular cosmic phenomena, such as type Ia supernovae. These events provide scientists with essential insights into stellar evolution, offering clues about the forces that govern the dynamics of binary systems and the fate of massive stars. In the heart of a red supergiant, a dramatic sequence of processes unfolds just before the star reaches the end of its life. After exhausting its nuclear fuel, the red supergiant progresses through several stages, fusing increasingly heavier elements. First, hydrogen is fused into helium, then helium into carbon and oxygen, and this continues until the core is predominantly made of iron. However, the fusion of iron presents a unique challenge. Unlike lighter elements, iron consumes energy rather than producing it. This leads to a halt in the star's ability to generate the outward pressure needed to counteract the immense gravitational forces pulling the core inward. Without this pressure, the delicate balance that has sustained the star for millions of years begins to falter, leading to a catastrophic collapse. The core's collapse occurs at an astonishingly fast rate, causing the star's core to become denser and hotter. Temperatures can soar to several billion degrees, triggering processes like photodisintegration, where energetic photons break apart iron nuclei into lighter particles, such as protons and neutrons. At the same time, the collapsing core is generating an immense amount of energy, building to a critical point. Once the core reaches a mass of about 3 times that of the Sun, it may transform into a neutron star, or if the mass is even greater, collapse further into a black hole. This collapse culminates in a massive explosion, a supernova, releasing extraordinary amounts of energy and expelling the star's outer layers into space. The supernova marks the violent end of the red supergiant, but also plays a crucial role in the recycling of elements throughout the universe. These explosions enrich the interstellar medium with heavier elements, providing the raw materials for the formation of new stars and planets. Thus, while the death of one star signals its end, it also marks the beginning of new cycles of stellar creation and destruction, perpetuating the ever-evolving dynamics of the cosmos. Reconciling quantum mechanics with general relativity stands as one of the most profound challenges in modern theoretical physics. These two towering pillars of our understanding of the universe have demonstrated immense success within their own realms. However, when scientists attempt to apply both frameworks simultaneously in extreme environments, such as near black holes or in the moments following the Big Bang, they run into fundamental incompatibilities. Quantum mechanics, which governs the behavior of the minuscule particles that make up the universe, operates at the scale of atoms and subatomic particles. In this realm, the world is governed by probabilities and uncertainties, concepts that seem strange when compared to the certainty of classical physics. On the other hand, general relativity, formulated by Albert Einstein, describes gravity not as a force, but as the curvature of space-time caused by mass and energy. It applies on a much grander scale, from planets and stars to entire galaxies, and describes a smooth, continuous fabric of space-time. But when we try to apply quantum mechanics to describe gravitational forces, it leads to a number of perplexing issues, particularly related to the concept of space-time itself. Where general relativity treats space-time as a smooth, unbroken continuum, quantum mechanics implies a more fragmented view, suggesting that space-time may be discrete at the smallest scales, particularly at the Planck scale. This is where the clash begins. One potential way forward lies in the search for a quantum theory of gravity. This is an ongoing area of research, and while many ideas have been proposed, none have yet provided a complete solution. One of the most well-known candidates for a unified theory is string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings are theorized to exist in higher dimensions, beyond the familiar 3 of space and 1 of time, offering a possible way to unify all the fundamental forces, including gravity, into a single framework. If successful, string theory could provide the long-sought-after theory of everything. Another promising approach is loop quantum gravity, which aims to quantize space-time itself. This theory posits that space-time is not a continuous fabric, but is instead made up of discrete units, like a vast network woven from loops. By applying quantum mechanics to the geometry of space-time, loop quantum gravity seeks to create a consistent theory that incorporates both quantum effects and gravitational interactions. Yet, even with these intriguing possibilities, both string theory and loop quantum gravity still face significant challenges, particularly in testing their predictions through experiments and observations. Despite these obstacles, scientists continue to search for ways to bridge the gap between the quantum and gravitational realms. Their efforts focus on understanding extreme phenomena, such as the evaporation of black holes, the dynamics of the early universe, and potential observational consequences that might shed light on this elusive unification. Though a complete reconciliation between quantum mechanics and general relativity remains an open question, the search for answers is one of the most exciting endeavors in modern physics, promising to deepen our understanding of the universe at its most fundamental level. One of the most fascinating and enigmatic phenomena in quantum mechanics is quantum entanglement. This phenomenon reveals an intricate, non-intuitive relationship between particles, where the quantum states of two or more particles become deeply linked. Once particles become entangled, the state of one particle cannot be described without reference to the state of the other, no matter the distance between them. This seemingly instantaneous connection, even across vast distances, was famously dubbed by Albert Einstein as spooky action at a distance. The true nature of entanglement is rooted in two fundamental principles: superposition and non-locality. When particles are entangled, they exist in a superposition of states, meaning they are not in a single definite state, but rather in multiple potential states at once. When one particle's state is measured, its state collapses into a definite value. Remarkably, this instantaneous collapse determines the state of the other entangled particle, regardless of how far apart they are. This phenomenon challenges our classical notions of information and causality, raising profound questions about the nature of reality itself. Experiments testing Bell's theorem have provided strong evidence that the correlations between entangled particles are far stronger than those predicted by classical physics. These results confirm that nature adheres to quantum principles that are radically different from our everyday experiences. The implications of quantum entanglement stretch beyond theoretical physics, with practical applications emerging in fields like quantum computing and quantum cryptography. By harnessing the properties of entangled particles, researchers are working to develop new technologies that could revolutionize computational power and create fundamentally secure communication methods. Thus, while quantum entanglement remains one of the most mysterious aspects of quantum mechanics, it stands as a testament to the intricate complexity and deep interconnections of the quantum world. It invites further exploration into the fundamental nature of reality, offering insights into the very fabric of existence itself. A central question in theoretical physics is whether space-time itself is quantized at the smallest scales. This is a crucial component in the ongoing quest to unite quantum mechanics with general relativity. As it stands, the general theory of relativity treats space-time as a smooth, continuous entity. But as researchers continue to probe the deepest structures of the universe, they wonder, could space-time, much like matter and energy, be composed of discrete quantized units at its most fundamental level? This question remains at the heart of some of the most exciting research in modern physics, with the potential to unlock a new understanding of how the universe operates at its basic level. At the frontier of our understanding of the universe, phenomena at incredibly small scales, on the order of the Planck length, about 1.6 times 10 to the power of negative 35 meters, pose significant challenges to our traditional descriptions of space and time. In fact, when we venture to these minuscule scales, our familiar notions of space-time may break down entirely. Some theoretical frameworks suggest that space-time itself could be quantized, existing in discrete units rather than as a smooth continuum. One such approach, loop quantum gravity, proposes that space-time is not continuous, but rather made up of tiny loops, each resembling a network that forms the very fabric of the universe. According to this theory, the geometric properties of space-time are quantized, meaning space and time could be represented by a collection of finite, indivisible elements, much like a digital image made up of pixels. This model seeks to reconcile the smooth, curved geometry of general relativity with the fundamentally discrete nature of quantum mechanics. Another prominent theory that touches on the possible quantization of spacetime is string theory. Unlike traditional models, which describe matter and forces in terms of point-like particles, string theory proposes that the fundamental building blocks of the universe are one-dimensional strings. These strings vibrate at specific frequencies, and their interactions form the particles and forces we observe. String theory operates in higher dimensional space, requiring up to 10 or even 11 dimensions to be mathematically consistent. In this framework, the extra dimensions, though essential for the theory's internal consistency, are thought to be compactified, curled up so tightly that they remain imperceptible to our senses and current technology. This higher dimensional model suggests that at the smallest scales, space-time itself could have a granular quantized structure, with the fabric of the universe potentially composed of minuscule vibrating strings. Despite the intriguing nature of these theories, the quantization of space-time has not yet been experimentally verified. The scales at which these effects would become noticeable are far beyond the reach of today's technology, making direct observation a formidable challenge. Nevertheless, as scientists continue to probe the deep intersections of gravity and quantum mechanics, the question of whether space-time is fundamentally quantized may one day be answered. Such discoveries could revolutionize our understanding of the universe at its most fundamental levels, offering new insights into the very nature of reality itself. In the conventional understanding of the universe, we live in a four-dimensional space-time framework. This model consists of three spatial dimensions: length, width, and height, and one time dimension. These four dimensions combine to form the well-known concept of space-time, where events are described by four coordinates: three that account for position in space, and one for the progression of time. This four-dimensional model aligns seamlessly with general relativity, our best theory of gravity, and reflects our everyday experience of the world. However, many theoretical physicists speculate that our universe might not be limited to these four dimensions. Some, like string theory, propose the existence of additional dimensions beyond the familiar ones we experience. According to string theory, the fundamental particles of the universe are not point-like objects, as in traditional physics, but rather tiny, vibrating strings that exist in higher dimensional space. In its most widely accepted formulations, string theory requires a total of 10 or even 11 dimensions to be mathematically consistent. These extra dimensions, however, are theorized to be compactified, curled up so tightly at scales far smaller than anything we can currently measure, that they remain hidden from direct observation. The possibility of extra dimensions opens up exciting avenues for unifying the fundamental forces of nature. These additional dimensions might help explain why gravity is so much weaker than the other fundamental forces, such as electromagnetism. They could also provide crucial insights into the mysteries of dark matter and dark energy, two of the most puzzling phenomena in modern physics. If proven true, these extra dimensions could reshape our understanding of everything from the origin of the universe to the forces that govern its evolution. While we are still far from confirming these theories experimentally, they offer a tantalizing glimpse into a universe far more complex and interconnected than we can currently comprehend. However, direct evidence for the existence of additional dimensions remains elusive. While experiments like those conducted at particle colliders, such as the Large Hadron Collider, aim to probe high-energy phenomena that could offer hints, the confirmation of these extra dimensions is still an open question. As research progresses and our understanding of the fundamental structure of the universe continues to evolve, we may one day uncover the true nature of dimensions beyond the observable three spatial ones and one temporal. This discovery could deepen our understanding of reality itself. Quantum decoherence offers a fascinating lens through which we can begin to understand the transition from the quantum to the classical world. It describes the process by which a quantum system loses its coherent quantum properties, shifting from a state of superposition to a classical mixture of states. This phenomenon occurs when the quantum system interacts with its environment, and in doing so, it reveals how classical properties, those familiar and tangible characteristics of everyday objects, emerge from the underlying quantum realm. Decoherence begins when a quantum system, initially existing in a superposition of multiple states, interacts with external environmental factors, whether particles, fields, or photons. As the system becomes entangled with its surroundings, information about the quantum states encoded within the superposition disperses into the environment. This interaction effectively measures the quantum system, leading to a loss of coherence as the quantum system's states lose their phase relationships. It is this process of coupling with the environment that triggers the transition from quantum to classical behavior. One of the most intriguing aspects of decoherence lies in the randomness and uncontrollability of the environmental influences. These unpredictable interactions cause the quantum system's original coherent superposition to gradually dissolve into an incoherent mixture of states, thereby diminishing the unique properties of quantum mechanics. The key takeaway is that once these environmental factors have interacted with the quantum system, it becomes impossible to recover the original quantum coherence. In this sense, decoherence serves as a bridge between the quantum and classical worlds, offering an explanation for why macroscopic objects behave according to classical laws despite being composed of quantum entities. It provides a mechanism that accounts for the determinism and locality we observe in classical physics, while also highlighting the probabilistic nature inherent to quantum systems. The study of decoherence not only deepens our understanding of the nature of reality, but also has significant implications in fields such as quantum computing and quantum information. In these areas, managing and maintaining coherence is critical for developing stable and functional quantum systems. At the heart of every measurement lies an element of uncertainty, and this uncertainty stems from both the tools we use and the very nature of what we are trying to measure. The concept of limits to precision is closely tied to two fundamental principles of physics: the limitations set by quantum mechanics and the noise inherent in measurement systems. As we push for more precise measurements, we inevitably encounter phenomena such as the Heisenberg uncertainty principle, which asserts that certain pairs of properties, like the position and momentum of a particle, cannot be known simultaneously with absolute precision. This principle sets a fundamental boundary on the accuracy with which we can measure specific quantum systems, thereby impacting the overall precision of scientific measurements. This uncertainty is not just a challenge, it's a defining feature of the quantum world, reminding us of the limits that govern not only our measuring tools, but the very fabric of reality itself. In the pursuit of knowledge, these limits force us to question what can be known, how precisely we can know it, and how these boundaries shape our understanding of the universe. The instruments we use to measure the universe around us, from telescopes to particle accelerators, have revolutionized our understanding. However, these tools come with their own set of limitations. Telescopes and accelerators are often constrained by factors like noise, calibration errors, or physical degradation over time. As we push further into the realm of precision, we often encounter the harsh reality that the limits of our instruments are, in many ways, the limits of our knowledge. These constraints are not just technical, they shape the very framework of what we can know about the cosmos. Yet, humanity's drive for ever finer details leads to constant innovation. Scientists have developed groundbreaking methods such as quantum sensors, which tap into the strange and counterintuitive principles of quantum mechanics to enhance measurement precision. Still, despite these advances, we must acknowledge an uncomfortable truth. The pursuit of perfect precision is an ongoing struggle, constantly hindered by both theoretical and practical limitations. These limitations are not simply roadblocks, but are intrinsic to the very nature of how we understand the universe. One of the greatest mysteries in modern physics centers on the emergence of gravity from quantum effects, a topic that remains largely unresolved. At its core, scientists are grappling with the relationship between two fundamental pillars of physics: general relativity and quantum mechanics. General relativity, which explains gravity as the curvature of space-time due to mass, stands in stark contrast to quantum mechanics, which governs the behavior of particles at the subatomic level. The challenge is immense. How do we reconcile these two powerful theories into a single, unified framework? An intriguing approach in this pursuit is the concept of quantum gravity. This theory proposes that space-time itself might not be a smooth, continuous entity, but rather a granular structure at the smallest scales, akin to how matter is composed of atoms. In this view, space-time could be made up of discrete units, or quanta, hinting that gravity might emerge from interactions at these fundamental levels. Just as temperature arises from the motion of countless particles, gravity might emerge from the collective effects of these microstates, leading to a new understanding of the force that governs our universe. Several theories are being explored to make sense of this quantum nature of space-time. Loop quantum gravity, for instance, suggests that the very fabric of space-time is woven from loops of quantum fields. Gravity, in this view, is the result of how these loops interact. Alternatively, string theory proposes that the fundamental building blocks of matter are not point-like particles, but tiny vibrating strings existing in multiple dimensions. In this framework, gravity is a natural byproduct of the interactions between these strings, with the graviton, a hypothetical particle, emerging as one of the force-carrying particles. Despite the appeal of these theories, there is a glaring issue: a lack of experimental evidence. Theoretical consensus is still elusive, and the complexity of these ideas underscores just how challenging it is to fully understand how gravity fits into the quantum landscape of the universe. Yet, as researchers continue to probe deeper into the mysteries of quantum mechanics and the nature of space-time, we edge ever closer to a more complete understanding of how gravity may emerge from the fundamental forces of nature. Turning to the larger scale picture, the ultimate fate of the universe has been a subject of intense fascination and speculation. While current observations suggest a few possible outcomes, including the Big Freeze or the Big Crunch, the true end of the universe remains uncertain. To understand these possibilities, we must first explore the ongoing expansion of the universe and the forces that drive it. The Big Freeze, or heat death, is often considered the most likely scenario. This theory is based on the current observations of the universe's accelerating expansion, which appears to be driven by an enigmatic force called dark energy. If this acceleration continues indefinitely, galaxies will drift farther and farther apart, stars will burn out and die, and the space between them will become colder and darker. In this frozen, empty future, the universe would be devoid of thermodynamic activity, slowly fading into nothingness over vast, unimaginable timescales. In contrast, the Big Crunch suggests a dramatic reversal of this trend. If the density of matter in the universe were high enough, gravitational forces could eventually overcome the expansion. The universe would then begin to contract, drawing all matter and energy into a final collapse, a singularity. This catastrophic event could either mark the end of everything or possibly set the stage for a new Big Bang, leading to the birth of a new universe. As we continue to explore these possibilities, the future of the cosmos remains one of the greatest unsolved mysteries in science. Whether it's the gradual cold death of the universe or a cataclysmic implosion, the ultimate fate of everything we know is still a question that will take humanity eons to answer. But with each new discovery, whether in the subatomic world or the vastness of space, we inch closer to uncovering the true nature of our existence and the universe's grand story. However, current evidence suggests that the universe's density is insufficient to trigger a collapse, which means the fate of the cosmos remains unclear. Beyond the two most widely discussed theories of the universe's end, such as the Big Crunch and heat death, other more speculative possibilities exist. One such idea is the Big Rip, where the universe's expansion accelerates uncontrollably, eventually tearing apart galaxies, stars, and even atomic structures. The ultimate fate of the universe is, and continues to be, a central mystery in cosmology. This enigma is largely dependent on the ongoing observations of the universe's expansion and the perplexing nature of dark energy. As scientists peer deeper into the cosmic unknown, these questions evolve, sparking both wonder and curiosity across the scientific community and among stargazers alike. To understand these theories, one must first grasp the concept of phase transitions, a well-established idea in condensed matter physics. We see it in action when substances like water shift between solid, liquid, and gaseous states based on temperature and pressure. But could the universe itself undergo such phase transitions? Some theorists propose that it has in fact already experienced dramatic shifts in its state. These transitions, they argue, could have occurred during pivotal moments early in the universe's history, such as the first few moments after the Big Bang. A prime example is the transition from quark-gluon plasma to hadronic matter. As the universe cooled, this transition led to the formation of protons and neutrons, the building blocks of matter. In much the same way as the universe continued to cool and expand, additional phase transitions may have contributed to the formation of galaxies, cosmic filaments, and the large-scale structures we observe today. Fast forward to modern discussions, and scientists are now considering the impact of potential phase transitions linked to the mysterious phenomenon of dark energy. If dark energy's density were to change dramatically, it could trigger a cosmic phase transition that shifts the universe's expansion in a completely new direction. Such a change might lead to outcomes like the Big Rip or introduce entirely unforeseen scenarios for the cosmos's ultimate fate. However, research in this area remains speculative, as understanding dark energy's true behavior is one of the greatest challenges in contemporary cosmology. The idea of cosmic phase transitions paints a dynamic portrait of the universe, not as a static entity, but as a constantly evolving system, capable of undergoing profound shifts under specific conditions. This exploration draws on both cosmology and high-energy physics, fueling exciting inquiries into the origins of the universe and its potential futures. As scientists continue to probe these mysteries, they strive to uncover the underlying principles that govern the cosmos and its perpetual cycles of transformation. Another concept that has captured the imagination of physicists is the formation of a true vacuum bubble within the universe. A true vacuum refers to a state with the absolute lowest possible energy, in stark contrast to the vacuum we are familiar with, which is filled with quantum fields and various forms of energy, including dark energy. The creation of a true vacuum bubble is a hypothetical and alarming scenario. If such a bubble were to emerge, the consequences would be far-reaching, transforming the fabric of reality itself. The true vacuum bubble represents a phase transition where the fundamental laws of physics may no longer apply. As this bubble expands at the speed of light, it would relentlessly consume all matter and energy in its path, creating a region where familiar physical laws cease to exist. Within the bubble, the universe could take on an entirely new set of rules, drastically different from the one we know. On the outside, the universe would be left with a void, as the bubble continues its rapid expansion. Should a true vacuum bubble encounter Earth, the planet would be obliterated almost instantaneously. There would be no time for escape, no time for preparation, just the unstoppable advance of this vacuum state. This scenario may sound like something pulled from the pages of science fiction, but it is rooted in theoretical frameworks of high-energy physics. The idea remains speculative, primarily because no direct evidence exists to suggest that such a true vacuum bubble is currently present or even likely to form in our universe. Nonetheless, it represents one of the more bizarre and unsettling possibilities in the ongoing study of the cosmos. However, it provides a compelling lens through which to explore the fundamental nature of our universe, its core properties, the mysteries of the vacuum states, and the potential for dramatic phenomena lurking within the very fabric of reality. The Stelliferous Era, which is the current epoch in the cosmic timeline, is marked by the intense brightness and ceaseless activity of stars. During this period, the formation, evolution, and eventual death of stars define the vibrancy of the universe, a dynamic, ever-shifting canvas of light and energy. The duration of the Stelliferous Era is estimated to span roughly 10 trillion years, a vast stretch of time that will eventually give way to a quieter phase, the Degenerate Era. As stars burn through their nuclear fuel, they play a crucial role in shaping the universe. Through their cycles, they release elements essential for the formation of planets and, ultimately, life itself. The distribution of elements will evolve, enriching the interstellar medium with heavier elements, products of stellar processes that serve as the building blocks for new worlds. As the Stelliferous Era progresses and stars exhaust their hydrogen fuel, the universe will see a profound shift. Fusion reactions in stars, which have long powered their shining light, will gradually cease as the hydrogen supply diminishes. Star formation will slow, and galaxies will deplete their gas reserves, signaling the twilight of the stellar epoch. Existing stars will undergo dramatic transformations. They may swell into red giants, collapse into white dwarfs, or explode as neutron stars or black holes, depending on their mass. In the waning years of the stelliferous era, the universe will quiet down. The brilliant bursts of new star formation will fade, leaving behind a far more subdued universe. This period, marked by the aging and death of stars, will be the precursor to the degenerate era, a time defined by the remnants of stars and the slow cooling of any remaining stellar objects. It is a time of profound stillness, as dark, inert remnants float through space, their once fiery cores now dimmed beyond recognition. As this era unfolds, the universe will be increasingly populated by black holes and subatomic particles, slowly drifting in a nearly empty, expanding cosmos. But the universe is not done with transformation. The degenerate era will eventually give way to the black hole era, a period when black holes will dominate the cosmic landscape. Through a process called Hawking radiation, black holes will slowly lose mass and energy over incredibly long time scales, potentially stretching into trillions of years. As they do, they will emit radiation, incrementally raising the temperature of the surrounding space, though this process is strikingly slow, particularly for the most massive black holes. The black hole era will ultimately come to an end when the last black hole evaporates. The universe, now devoid of its earlier cosmic structures, such as stars and galaxies, will transition into the dark era. This period is marked by a universe completely void of light or heat sources, with only the faintest of remnants left to mark the passage of time. The temperature will approach absolute zero as the universe cools, settling into an almost uniform state of desolation and cold. During this time, entropy will continue to increase, leading to a nearly static and barren cosmos. Matter will decay into lighter particles, following processes such as proton decay, a phenomenon suggested by various grand unified theories. This distant future will be a universe emptied of its previous vibrancy, a dark, sparse expanse, no longer filled with the light of stars or the swirling energies of galaxies. Instead, it will be a fading echo of the dynamic cosmos that once thrived, raising profound questions about the nature of existence itself. The end of black holes signals the culmination of this cosmic journey, a universe where all potential for activity has been exhausted, leaving behind a hauntingly quiet and lifeless void. This speculative view of the far future deepens our understanding of the universe's eventual fate and the physical laws that will govern its slow, inexorable evolution. The very idea of an endless cosmic cycle is a concept that has captivated both scientists and philosophers. It suggests that instead of a linear progression from a singular beginning to an eventual end, the universe might follow an eternal sequence of expansion and contraction, cycles that could repeat endlessly. One of the most intriguing models of this cyclical universe comes from the theory of the epirotic universe. This hypothesis posits that our universe may have arisen from the collision of two higher dimensional objects, or branes, in a multi-dimensional space. This collision, akin to a cosmic bang, would have triggered a new phase of expansion, eventually halting and then contracting in a big crunch, leading to yet another collision that would ignite a new cycle of expansion. Each cycle would give rise to a universe similar to, yet distinct from, the previous one. Another perspective on the cyclical universe emerges from the realm of quantum gravity, where physicists explore how the laws of quantum mechanics might allow for bouncing universes. In these models, the universe could experience a singularity before the Big Bang, transitioning smoothly from contraction to expansion in a continuous cycle, without a definitive beginning or end. While the cyclical universe presents an alternative to current cosmological models, many questions remain unanswered. The dynamics of cosmic expansion, the behavior of dark energy, and the implications of thermodynamics across countless cycles still require deep exploration. The full understanding of these phenomena will likely shape our future understanding of the universe's true nature and its eternal journey across time. The nature of entropy is a fundamental element in understanding the fate of our universe, particularly when considering models like the cyclical universe. According to the second law of thermodynamics, disorder tends to increase over time. This presents a challenge for any theory that proposes a strictly cyclical model of the universe. To account for the inevitable rise in entropy, mechanisms that could either reset or manage this growing disorder would have to be considered. Exploring a cyclical universe, therefore, not only invites speculation about the past and future, but also forces us to rethink key concepts like time, existence, and the ultimate destiny of cosmic evolution. As research pushes forward, one of the central questions in theoretical physics remains whether our universe is part of an endless cycle. This remains a pivotal inquiry at the frontier of cosmological exploration, as scientists attempt to answer whether the cosmos follows a repetitive pattern or if it will eventually reach an irreversible end. The quest to understand this cycle could reshape our entire understanding of space, time, and the nature of reality itself. Meanwhile, the concept of parallel universes, often referred to as the multiverse, has emerged as a captivating area of study in modern cosmology and theoretical physics. While it might sound like pure science fiction, several interpretations of quantum mechanics and cosmological theories propose that parallel universes could indeed exist. One of the leading ideas supporting this possibility comes from the many worlds interpretation of quantum mechanics. This theory suggests that every time a quantum event occurs with multiple possible outcomes, the universe splits into branches. Each possible outcome unfolds in its own separate universe, giving rise to an infinite number of parallel realities coexisting simultaneously. In this framework, every decision, every random event creates diverging paths, which could lead to a vast, intricate tapestry of alternate realities. These realities would encompass every conceivable possibility, an ever-expanding array of worlds that might range from incredibly similar to our own to entirely different in ways we cannot even imagine. Additionally, a theoretical model from inflationary cosmology introduces another form of parallel universes. In the wake of the Big Bang, the universe underwent rapid expansion, a process known as inflation. During this expansion, tiny fluctuations in the early universe could have caused regions of space to develop different physical properties. These variations might lead to the creation of bubble universes, each with its own distinct set of physical laws or constants. This model implies that our observable universe might merely be one bubble in a vast cosmic foam, with each bubble universe evolving independently, potentially hosting difference of life, matter, and even laws of physics. These concepts challenge our conventional understanding of the universe, offering a fascinating glimpse into the possibilities that exist beyond our own cosmic bubble. Whether it is the idea of a cyclical universe or the existence of a multiverse, the boundaries of reality are expanding in ways we never thought possible, propelling us further into the unknown realms of science and philosophy. In the realms of cutting-edge physics, some string theory models propose the existence of extra dimensions beyond the three-dimensional space we experience daily. These additional dimensions could enable radically different configurations of fundamental forces and particles, giving rise to entirely distinct regions that could be interpreted as separate universes. The notion of parallel universes, or the multiverse, has captivated both the imagination and the intellect. However, despite its allure, the evidence supporting the existence of such universes remains stubbornly elusive. Many in the scientific community view the idea of the multiverse as highly speculative. It stirs both excitement and skepticism, and rightly so, given that it stretches the limits of our current understanding. As research progresses with new insights emerging from quantum mechanics, cosmology, and our exploration of reality itself, the question of whether parallel universes exist continues to haunt the minds of theorists and laypeople alike. Each discovery offers a fresh lens through which we might view the very fabric of existence and raises deeper questions about what reality truly is. One of the most intriguing aspects of this multiverse concept is how different universes, if they do exist, might interact with one another. How do fundamental forces and laws transcend the boundaries of their own domain? How might universes interact across the vast, unfathomable space that separates them? The answers are not simple, and most theories suggest speculative and highly complex mechanisms, often incorporating elements of quantum mechanics, general relativity, and advanced ideas such as string theory. A compelling interpretation comes from the many worlds view of quantum mechanics, which presents a scenario where quantum events, like particles behaving in various unpredictable ways, create separate branches of reality. These branches represent different possible outcomes, each forming its own independent universe. In this view, the universes do not influence one another. They exist separately and in isolation. Interactions, as we understand them in our own universe, simply do not occur across these parallel realities. This model paints a picture of a multiverse that is, in essence, a collection of parallel timelines, each self-contained and impervious to the others. On the other hand, the idea of bubble universes takes a different approach. Arising from inflationary cosmology, this theory proposes that our universe may be one of many, all forming in a process similar to the bubbles in a pot of boiling water. Each universe could represent a distinct region of space, created during the rapid expansion that occurred in the early moments of the cosmos. If these bubble universes exist within a higher dimensional space, it's conceivable that they could interact, albeit under very specific conditions. Such interactions might manifest as gravitational effects, potentially causing the merging or even the collision of bubbles. In theory, these events could alter the physical properties of the involved universes and perhaps leave detectable signs in our own universe. However, much like other multiverse theories, this concept remains speculative, awaiting validation through observation or experimental data. In the end, the quest to understand whether parallel universes exist and how they might interact, if they do, is one that straddles the boundary between the known and the unknown. As our tools for exploring the cosmos become ever more sophisticated and our theories more refined, the multiverse remains a tantalizing possibility. However, whether we will ever gather the evidence needed to confirm or deny its existence remains to be seen. In the meantime, the idea of parallel universes continues to spark philosophical debates and scientific inquiries that push the very limits of what we understand about the universe and our place within it. String theory introduces a new layer of complexity to our understanding of the cosmos, suggesting the existence of extra dimensions within the fabric of reality. In this framework, our universe might not be the sole entity in existence. Instead, multiple universes could be represented as brains, multidimensional objects that interact with one another in a higher dimensional space. The possibility that these brains could collide is both awe-inspiring and unsettling. Such an interaction could lead to the creation of entirely new physical phenomena, or perhaps even give rise to entirely new universes. The dynamics of these collisions could reshape the very fabric of the physical laws that govern the universes involved, altering fundamental constants and pushing the boundaries of what we understand to be possible. However, despite these intriguing possibilities, the idea of interuniversal interactions remains largely speculative. At present, there is no empirical evidence supporting the existence of parallel universes, let alone any established framework that can demonstrate how these universes might interact. Still, these questions captivate both scientists and philosophers alike, sparking debates about the nature of reality, coexistence, and the complexity of existence within a potentially expansive multiverse. As research progresses, the curiosity surrounding these interactions continues to challenge our understanding of the cosmos, drawing us deeper into the mystery of whether multiple universes could exist and how they might behave. The question of whether we could ever detect evidence of other universes remains one of the most captivating within cosmology and theoretical physics. While the concept of a multiverse is tantalizing, the challenges involved in gathering definitive proof of its existence are monumental. Several theoretical approaches have been proposed, suggesting possible pathways for detecting these elusive realms. One such potential avenue lies within the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. Some physicists theorize that collisions between bubble universes or interactions between different cosmic regions could leave subtle imprints in this radiation. If our universe is merely one among many, these interactions might leave detectable signatures, potentially manifesting as irregularities in the temperature fluctuations of the CMB. While some studies have endeavored to find these anomalies, conclusive evidence remains frustratingly elusive. Another possibility is the detection of gravitational waves, ripples in spacetime caused by cataclysmic cosmic events. Certain models of the multiverse suggest that significant events, such as the merging of bubble universes or collisions between cosmic structures, could generate gravitational waves with unique signatures. If future advancements in gravitational wave detectors are successful, they could offer scientists a way to observe signals that indicate such extraordinary cosmic events, providing compelling indirect evidence of the existence of other universes. Quantum mechanics, too, provides a window into the potential connections between universes. Experiments exploring phenomena like quantum entanglement might reveal whether multiple universes subtly influence one another. If scientists detect discrepancies or behaviors that cannot be explained by our current understanding of quantum mechanics, this might offer tantalizing hints that interactions with other universes are at play. Yet, despite these intriguing possibilities, direct evidence for the existence of other universes remains elusive. The very nature of our observational limits makes this task incredibly difficult. Current scientific methodologies depend heavily on testing hypotheses within the boundaries of our own universe. This reliance on experimental evidence gathered within our observable reality makes it inherently challenging to confirm or deny the existence of other universes. As such, the multiverse remains a speculative and fascinating concept, one that invites excitement, but also demands caution when drawing conclusions. As science advances, researchers continue to explore new pathways to investigate the multiverse idea, pushing the boundaries of what we know about the cosmos and our place within it. The notion of the multiverse encompasses a variety of theoretical frameworks, each proposing different types of universes that could exist alongside or within our own. While definitions and categorizations vary, scientists generally describe several broad categories of multiverses based on their origins and underlying mechanisms. To me, prominent model is the inflationary multiverse, which arises from the theory of cosmic inflation. This model suggests that in the moments following the Big Bang, the universe expanded at an extraordinarily rapid rate. During this expansion, different regions of space could have stopped inflating at different times, creating bubbles or pockets of space. Each of these bubbles could evolve into a distinct universe with its own unique physical properties. The inflationary multiverse proposes that there may be an infinite number of such universes, each with different configurations of fundamental forces, dimensions, and particles. Another well-known category is the many worlds interpretation of quantum mechanics. In this view, every time a quantum event occurs with multiple possible outcomes, the universe splits, creating a new reality for each possible result. This interpretation suggests that an immense, possibly infinite number of parallel universes exists, each one corresponding to a different outcome based on quantum decisions. These universes coexist, but they do not interact with one another. Each branch represents a distinct version of reality, from everyday choices to the microscopic interactions of particles. While the notion of multiple universes might seem fantastical, it raises profound questions about the nature of reality itself. As our understanding of quantum mechanics, cosmology, and string theory continues to evolve, the idea that we live within an infinitely vast multiverse may not be as outlandish as it once seemed. Nevertheless, the evidence to confirm this theory remains, for now, just beyond our reach. In recent years, theories emerging from string theory have sparked profound questions about the very fabric of our reality. These theories suggest that the fundamental nature of particles may lie within higher dimensions, dimensions that, while invisible to us, could shape the laws of the universe in ways we are only beginning to understand. In certain configurations, these extra dimensions may give rise to different vacua, distinct states of energy, each one leading to universes with their own unique characteristics. The result? A vast and potentially infinite landscape of universes, each governed by its own set of physical laws. This concept forms the basis of what's known as the string theory multiverse. But the possibilities don't stop there. Some variations of these theories suggest that the multiverse could be so expansive that it encompasses a nearly infinite number of universes, each with its own physical constants and laws of nature. Some universes might have vastly different properties than ours, creating worlds where the fundamental forces of nature behave in radically different ways. In this framework, it's even possible that our universe is simply one among many, and the specific conditions that allow life to thrive here are extraordinarily rare, one small piece in a giant cosmic puzzle. This brings us to the concept of the anthropic multiverse. According to this perspective, the reason our universe seems uniquely suited for life is that we happen to be living in one of the few universes where conditions are just right for life to emerge. In other words, the universe we observe may be a statistical anomaly, one where the conditions for life just so happen to be fine-tuned. The anthropic principle suggests that, since we are part of this universe, we are only capable of observing the physical laws and constants that support our existence. It's a deeply humbling thought. We exist because we live in a universe that can support life, but we may never know how many other uninhabitable realities surround us. However, despite the elegance of these theories, there is a glaring absence of empirical evidence to support them. While the field of theoretical physics has made extraordinary strides, these ideas remain speculative, an exciting frontier that challenges the boundaries of human knowledge. As our research deepens, the idea of exploring multiple, vastly different universes continues to push the limits of our understanding of the cosmos. It forces us to ask fundamental questions about the nature of existence and our place within this cosmic expanse. What if the laws of physics in other universes were not only different from ours, but completely incompatible with the very structure of our reality? Some theories propose that the fundamental constants, such as the speed of light or the strength of gravity, might not be universal. Instead, they could vary dramatically depending on the universe. In the inflationary multiverse, for instance, bubble universes may each have their own set of physical laws and constants, leading to environments where matter behaves in unexpected ways. In such universes, stars might never form, or the very idea of chemistry might be unrecognizable to us. The implications of this are vast. A universe where the constants of nature differ could harbor entirely alien forms of matter and life, or it might be completely inhospitable to the formation of structures like galaxies, stars, or planets. The possibilities are as awe-inspiring as they are mind-boggling. And that's just one of the many ways that the multiverse could manifest itself. Another intriguing possibility comes from the many worlds interpretation of quantum mechanics, which suggests that every quantum event spawns a new branch of reality. In this view, every possible outcome of a quantum event exists in a separate universe. While some laws of physics might remain consistent across these different worlds, the events and outcomes they experience could lead to radically distinct realities. One universe might experience entirely different types of matter, while another might operate with a completely redefined notion of time and causality. String theory further enriches this picture. By suggesting the existence of extra dimensions and various vacuum states, it opens up the possibility that universal constants like the strength of electromagnetic forces or the nature of gravity could change based on the configuration of these hidden dimensions. As these variations unfold, they could create environments where the behaviors of matter, energy, or even time itself behave unpredictably, leading to universes that seem utterly alien to us. In one universe, gravity might be so weak that large-scale structures like galaxies never form, while in another, the laws of time could operate in ways we can't even begin to imagine. Perhaps most mind-bending of all, some theorists have even proposed universes where the laws of physics are so different that the very concept of time, or even causality, might break down entirely. In these universes, the framework we rely on to understand the universe might not even apply. These realities could be so foreign that they defy our comprehension, leaving us to wonder what they might look like if they exist at all. While these ideas remain speculative for now, they prompt some of the deepest questions we can ask about reality. What if the rules governing existence, rules that seem so fixed and immutable to us, are actually subject to change? What if the cosmos is not the orderly, predictable system we assume, but instead a chaotic, ever-evolving realm where the laws of physics vary across infinite dimensions? These theories offer a radically different view of the universe, one that challenges our most basic assumptions about the nature of reality itself. In parallel with these cosmological questions, the idea of strange matter offers a tantalizing glimpse into the unknown properties of the universe. Strange matter is a theoretical form of matter composed of strange quarks, one of the heavier varieties of fundamental particles. These quarks are thought to exist in extreme environments, such as the cores of neutron stars, the dense remnants of supernova explosions. Here, gravity is so intense that matter is compressed to extraordinary levels, and it's hypothesized that quarks, usually confined within protons and neutrons, might break free and combine in strange new ways, leading to the formation of strange matter. This concept, still theoretical, could be key to understanding the behavior of matter in some of the most extreme and enigmatic environments in the universe. While it remains unobserved in nature, theoretical models suggest that strange matter could be a critical component of the processes that govern high-energy physics, especially in astrophysical contexts like neutron stars and black holes. As our understanding of the cosmos deepens, it's becoming increasingly clear that the universe is far more complex and mysterious than we ever imagined. The idea of the multiverse and the countless possibilities it holds invites us to think beyond the limits of our current knowledge and reconsider the very nature of reality. In the end, these theories, whether proven or not, push us to imagine a cosmos far richer, stranger, and more diverse than we could ever have dreamed. Strange matter, a concept that both intrigues and challenges our understanding of the universe, presents a host of captivating possibilities, especially in relation to its stability when compared to ordinary nuclear matter. If strange matter were found to be stable, it could revolutionize our perception of stellar objects. One of the most remarkable implications is the potential existence of strange stars, hypothetical cosmic bodies entirely composed of strange quarks. These stars might possess radically different properties from the neutron stars we know today, including unexpected behaviors in terms of mass, size, and stability. Equally fascinating is the idea of strangelets, tiny lumps of strange matter that could, in theory, exist independently. If these strangelets were to come into contact with ordinary matter, they might trigger a transformation, converting the regular matter into strange matter. This potential for a catastrophic conversion raises significant concerns, though it's important to note that these scenarios remain speculative for now. The allure of strange matter lies in its mysterious nature, but much more research is needed to determine its actual existence and its potential properties. At the forefront of this research are particle accelerators like the Large Hadron Collider, LHC, where scientists are pushing the boundaries of our understanding of quarks and other fundamental particles. By studying matter under extreme conditions, researchers are gradually uncovering how matter behaves at its most fundamental level. The ongoing exploration of strange matter could provide profound insights into the universe's most enigmatic phenomena and help us comprehend the very building blocks of the cosmos. But strange matter is only part of the picture. In the early universe, just moments after the Big Bang, another extreme state of matter existed, quark-gluon plasma. This state, believed to have been present before quarks and gluons combined to form protons and neutrons, possessed characteristics that make it drastically different from anything we encounter in our everyday lives. Quark-gluon plasma existed at temperatures and densities far beyond anything we've ever witnessed, often exceeding millions of degrees Celsius. Under these intense conditions, quarks and gluons, which are normally confined within particles like protons and neutrons, were free to move independently. This liberation created a fluid-like medium filled with highly energetic particles, offering a snapshot of the conditions that existed in the universe's infancy. One of the most intriguing features of quark-gluon plasma is its behavior under cooling conditions. As the plasma cools, the energy density decreases, and the fundamental strong force, which normally binds quarks together, becomes progressively stronger. Eventually, it forces quarks to remain confined within hadrons, particles like protons and neutrons. This transition is a key moment in the evolution of the universe, as it marks the shift from a free-roaming quark-gluon state to the more familiar hadronic matter we see today. Moreover, quark-gluon plasma exhibits another remarkable property: its behavior as a nearly perfect fluid. Despite the extreme conditions, quark-gluon plasma shows surprisingly low viscosity, allowing it to flow with minimal resistance. This near-perfect fluidity suggests that, even in such chaotic environments, quarks and gluons still interact in a collective manner, similar to how particles behave in ordinary fluids. These extraordinary properties have been observed in high-energy experiments, including those conducted at the LHC and the Relativistic Heavy Ion Collider, RHIC, where scientists recreate conditions close to those of the early universe in order to study these exotic states of matter. In conclusion, while both strange matter and quark-gluon plasma remain largely theoretical, their exploration provides us with a deeper understanding of the universe's earliest moments and the fundamental forces that shape it. With each new discovery, we move closer to unlocking the mysteries of the cosmos and revealing the true nature of matter itself. At the heart of our universe, hidden beneath the veil of ordinary matter, lies an enigmatic state of matter, quark-gluon plasma, QGP. A substance so alien and extreme that its very existence unlocks the deepest secrets of the cosmos. The study of this exotic matter offers an unprecedented opportunity to probe the fundamental forces that shape everything around us. By examining its unique properties and behaviors, scientists can peer into the very forces that govern the universe's most ancient moments, when conditions were so extreme that space-time itself was still in its infancy. QGP, a state that existed briefly after the Big Bang, allows researchers to explore the strong force, one of the four fundamental forces of nature. This force holds atomic nuclei together, but when matter is compressed and heated to extraordinary temperatures, the very fabric of the universe begins to unravel, revealing the intricate dynamics at play during the universe's earliest epoch. As researchers continue to accelerate particles to near-light speeds and collide them, these intense experiments might soon offer the answers to questions that have puzzled scientists for centuries. What is the true nature of matter? How did the cosmos evolve from a primordial soup into the vast expanse we observe today? But quark-gluon plasma is not the only exotic matter that sparks the curiosity of scientists. Among the most captivating concepts are those involving negative mass, or negative energy density, properties that seem to defy the laws of ordinary physics. These unusual characteristics set exotic matter apart from the substance we interact with daily, prompting physicists to wonder, could stable forms of this matter exist in the cosmos, hidden in distant galaxies, or under conditions so extreme that we have yet to replicate them on Earth? Theoretical physicists have long speculated about the potential applications of such exotic matter, particularly when it comes to mind-bending concepts like wormholes or warp drives. These fascinating possibilities, which could allow for faster-than-light travel or even open gateways between different dimensions, rely heavily on the existence of exotic matter to remain stable. For instance, a wormhole, a theoretical tunnel connecting distant points in space-time, could not exist without exotic matter to stabilize its throat and prevent it from collapsing under the immense gravitational forces at play. If stable configurations of exotic matter do indeed exist, they could be the key to unlocking interstellar travel, offering the promise of exploring far-flung regions of the universe, or even traveling between entirely different universes. However, the real challenge is not in conceiving these extraordinary possibilities, but in detecting and studying such matter. The universe is vast and full of complexities, and our ability to observe and understand it is limited by both our technology and our imagination. Still, advancements in particle physics, astronomy, and cosmology may one day bring these hidden forms of matter into the light, offering profound insights into the nature of the universe itself and reshaping the foundations of physics. In the ongoing pursuit of knowledge, the search for exotic matter compels us to question everything we thought we knew about the cosmos. Each discovery in this field brings us one step closer to understanding the very forces that govern our reality, revealing the incredible variety of phenomena that make up our universe. And while the answers we seek may not come easily, it's in these unanswered questions where we often find the most unexpected revelations. But the search for the unknown doesn't stop there. Extreme pressures in the universe lead to transformations in matter that challenge everything we understand about its behavior. Under such conditions, forces that bind atoms and molecules together are pushed to their limits, and materials can undergo radical changes. As pressure increases, atoms are forced closer together, causing materials to become denser and transition into forms unlike anything we experience on Earth. For instance, take carbon. Under extreme pressure, the soft, flaky form of graphite can be converted into the hardest material known to humanity, diamond. This transformation occurs because the atoms in graphite rearrange themselves into a more compact structure, stabilized by the immense pressure. Such changes aren't just limited to everyday materials, though. In the heart of giant gas planets like Jupiter, hydrogen, normally a gas, can become metallic hydrogen under the crushing pressure found there. This exotic form of hydrogen is believed to conduct electricity with remarkable efficiency and could play a crucial role in the behavior of these distant worlds. The study of these extreme conditions not only sheds light on the behavior of matter, but also offers insights into the formation and evolution of celestial bodies. For example, in the dense core of a neutron star, matter is compressed to densities so high that it surpasses even the density of atomic nuclei. These stars, the remnants of exploded supernovae, represent some of the densest objects in the universe, where gravity is so powerful that even light cannot escape their grasp. At the heart of neutron stars, matter is compressed beyond comprehension, creating environments where the usual laws of physics seem to break down. Neutrons, normally stable particles, become the fundamental building blocks of these stellar remnants. And in these extraordinary conditions, scientists believe that new, undiscovered forms of matter may exist, offering tantalizing clues to the very fabric of the universe. In these extreme environments, the very nature of matter and energy is transformed, pushing the boundaries of our understanding. As technology advances and our ability to study the universe improves, these revelations may lead to profound shifts in how we perceive the cosmos and our place within it. The universe, with all its awe-inspiring complexity and boundless mysteries, invites us to continue our search for answers. Each discovery in the study of matter, whether in the form of quark-gluon plasma, exotic states of matter, or the extreme environments of neutron stars, helps us take one more step closer to unraveling the fundamental truths that govern the universe. And as we push the limits of our exploration, we are reminded that the universe is full of surprises, waiting to be discovered. As pressure within neutron stars continues to rise, it reaches levels far beyond typical neutron densities, causing matter to transition into states that remain largely unexplored and poorly understood. Among the most intriguing possibilities is the formation of quark-gluon plasma, a unique state where quarks and gluons, the fundamental building blocks of protons and neutrons, no longer remain confined within these particles, but instead exist freely. This phase would represent a radically different form of matter, one that could yield important insights into the behavior of particles at extreme conditions. But that's not all. Theoretical physicists also propose the existence of even more exotic phases of matter, such as hyperons or meson condensed states, which could manifest under the extreme pressures found in neutron stars. Hyperons, particles containing strange quarks, might significantly alter the characteristics of neutron star matter, presenting a completely new set of challenges to our current models. These bizarre phases of matter could influence not only the structure and stability of neutron stars, but also their lifespan and behavior, leading to stars that behave in ways traditional models cannot predict. Exploring these unseen states of matter is far more than an academic pursuit. It is a crucial step toward understanding the fundamental workings of the universe. The study of neutron stars, especially through gravitational waves and electromagnetic signals, offers vital clues to what lies deep within these cosmic objects. As research advances, the possibility of uncovering new and strange states of matter at the very cores of neutron stars presents a tantalizing frontier in modern physics and cosmology. These discoveries could challenge our most fundamental assumptions about what matter truly is. In parallel, the theory of cosmic inflation presents an equally fascinating puzzle about the origins and early dynamics of the universe itself. Cosmic inflation proposes that the universe expanded exponentially in a fraction of a second, just moments after the Big Bang. This idea emerged to explain a variety of perplexing observations, including the large-scale homogeneity, isotropy, and the uniformity of the cosmic microwave background radiation. Though the exact mechanism behind inflation is still a subject of ongoing research, several theories have been suggested to account for this rapid expansion. One such theory involves a hypothetical field known as the inflaton field, which could have been responsible for the dramatic energy fluctuations that triggered inflation. In this scenario, the universe began in an extremely dense, high-energy state, with particles and energy packed together tightly. As the inflaton field evolved, it produced a repulsive force that caused the universe to expand at an extraordinary rate. This rapid expansion would have smoothed out any irregularities, setting the stage for the formation of a homogeneous universe that we observe today. Another theory suggests that cosmic inflation might have been driven by a phase transition within the fabric of the universe. Just as water changes states when heated, the universe itself could have undergone a phase transition as it cooled, releasing massive amounts of energy and propelling the inflationary expansion. Researchers are investigating whether this energy release occurred as the universe transitioned from a high-energy state to one of lower energy density, fundamentally altering the course of cosmic evolution. Despite these theories, a consensus on the specific cause of cosmic inflation remains elusive. However, astronomers continue to gather evidence through observations of the cosmic microwave background radiation, which bears the imprints of the inflationary period. Additionally, studies of the universe's large-scale structure contribute to a growing understanding of how inflation might have shaped the universe. As both observational technology and theoretical models continue to advance, the quest to uncover the origins and mechanics of cosmic inflation remains one of the most exciting and vital areas of modern cosmology, promising profound insights into the very nature of the universe itself. Cosmic inflation, the theory describing the rapid expansion of the universe just moments after the Big Bang, stands as one of the most pivotal events in the history of the cosmos. It was a brief yet explosive period during which space itself stretched out at an unimaginable rate, smoothing and flattening the universe to an almost perfect uniformity. But just as rapidly as inflation began, it came to an end. This cessation wasn't a random event, but a consequence of the dynamics of the inflaton field, the mysterious energy field that drove this extraordinary expansion. At first, the inflaton field pushed the universe to inflate exponentially, expanding faster than light could travel. However, as inflation progressed, something remarkable began to occur. The energy within the inflaton field began to change. Instead of maintaining a constant energy density, the field started to cool and evolve. This cooling led to a dramatic shift, with the energy density of the inflaton field slowly dissipating over time. Once the field hit a critical energy threshold, a phase transition occurred. This phase transition converted some of the field's potential energy into matter and radiation, triggering the phenomenon we call reheating. Reheating was more than just a period of energy release. It was the moment when the universe filled with particles, laying the foundation for the cosmos we observe today. These particles formed the building blocks of everything: galaxies, stars, and eventually life itself. The end of inflation marked the point where the universe, once a rapidly inflating and nearly featureless expanse, became a place where gravity began to dominate the dynamics. The smooth, flat space-time that inflation had created gradually gave way to a universe where structure could form, galaxies and clusters of galaxies slowly taking shape over billions of years. Yet, despite the clarity of inflation's end, the precise reasons for its cessation remain a mystery. Scientists have developed a range of models to explain this transition, each suggesting different dynamics for the inflaton field. Some theorists propose that additional interactions or even other fields may have played a role in halting inflation. As our observational tools improve, researchers hope to uncover deeper insights into the nature of the inflaton field and what conditions prompted it to stop. This question, why did inflation stop, is not just academic. It holds the potential to unlock a greater understanding of the universe's formative moments, those first few moments after the Big Bang. But there's another equally fascinating question that has emerged. Could cosmic inflation start again? While inflation as we understand it was a brief and intense period, the idea that it might resume in certain parts of the universe is a tantalizing one. The concept of eternal inflation suggests that while inflation has ended in the observable universe, it could continue indefinitely in some regions. In this model, quantum fluctuations could trigger localized patches of inflation, creating what's known as a multiverse, a cosmos containing many different universes, each with its own inflationary history. Within this framework, our universe, though homogeneous and isotropic, might just be one small part of a much larger and still inflating cosmos. For inflation to reignite in a particular region, certain conditions must be met. A field like the inflaton would need to re-emerge, capable of generating enough energy density to trigger a new round of exponential expansion. However, this scenario remains speculative, as it would require dramatic shifts in the energy fields that govern the universe. If inflation were to restart in some part of the cosmos, the consequences would be profound. This new burst of inflation could lead to the creation of entirely new universes, or pockets of space, that would evolve independently of our own. These regions could even separate from our observable universe, leading to a reality far beyond what we can currently comprehend. This raises fundamental questions about the nature of the universe itself. How stable is our reality? What does the future hold for cosmic expansion? Ultimately, while the idea of inflation restarting is a fascinating one, it remains largely within the realm of theoretical physics. The conditions and mechanisms required for such an event are not yet understood, and as such, it remains a topic of ongoing research and speculation. But this line of inquiry fuels our curiosity about the universe's most fundamental nature. Quantum fluctuations played an essential role in shaping the large-scale structure of the universe we observe today. These tiny, random variations in energy, which stem from the principles of quantum mechanics, occurred during the inflationary period of the universe. As the universe expanded exponentially, these fluctuations were stretched beyond their original scale, becoming frozen into the very fabric of space-time. Over time, these small variations in density became more pronounced, laying the groundwork for the formation of galaxies and other large-scale structures. Regions with slightly higher density exerted stronger gravitational forces, attracting more matter and eventually forming the complex cosmic structures we see across the universe. These fluctuations, initially minuscule and random, set the stage for the universe's grandest formations, echoing the remarkable journey from a nearly featureless, rapidly expanding universe to the complex and diverse cosmos we inhabit today. Conversely, regions with lower density experience less gravitational attraction, creating a vacuum of matter. As inflation came to an end, the energy from these fluctuations transformed into matter and radiation during the reheating phase. As the universe cooled, slight differences in density sparked a gravitational collapse of matter in the areas of higher density. Over time, this process culminated in the formation of galaxies, clusters, and superclusters, giving rise to the vast and intricate web of cosmic structures that we observe today. These quantum fluctuations, in essence, acted as the initial seeds around which everything we see in the universe today has grown. Without inflation, these fluctuations would not have expanded enough to leave an impact once the universe began to cool. The intricate dance between quantum mechanics and large-scale cosmic dynamics highlights the deep connection between the microcosm of subatomic particles and the macrocosm of cosmic structures. It reveals how fundamental processes govern the evolution of the universe on all scales. The concept of regions of space still undergoing inflation connects to the theory of eternal inflation, which proposes that while our observable universe underwent a defined period of rapid expansion, inflation may continue in isolated regions beyond our view. According to this model, the universe forms part of a vast multiverse, where different regions experience inflation at different times, creating a patchwork of universes that vary in their physical properties. In scenarios of eternal inflation, quantum fluctuations could trigger localized pockets of inflation that persist even after inflation ceases in adjacent areas. These pockets would continue to expand exponentially while the surrounding regions evolve into more conventional cosmological states. This means that while we observe a uniform and isotropic universe, there could be other regions, potentially infinite in number, that remain in an inflationary state. The implications of this are profound. If such regions exist, new universes could form through a process known as bubbles of inflation. In this model, each bubble would represent a unique universe, governed by its own distinct physical laws and conditions. The very idea that inflationary regions could persist opens the door to the possibility of a multiverse, where multiple realities coexist, each evolving according to its own rules. While these ideas provide fertile ground for theoretical exploration, they currently lacked observational evidence. The main challenge lies in the fact that these inflationary regions would be entirely disconnected from our observable universe, making it difficult, if not impossible, to detect or study them directly. Still, ongoing research in cosmology, along with advancements in observational techniques, may eventually help delineate the boundaries of our universe and shed light on the nature of inflation and the potential existence of an inflating multiverse. Exploring these concepts remains an exciting frontier, raising fundamental questions about the very nature of reality itself. Time, as we experience it, flows in a single direction, commonly known as the arrow of time. This directionality is observed at all scales, from the microscopic world of particles to the cosmic scale of galaxies. The driving force behind this phenomenon is the second law of thermodynamics, which states that entropy, the measure of disorder in a system, tends to increase over time. This naturally leads to a progression from states of lower entropy to higher entropy, giving rise to a forward-moving arrow of time that aligns with our everyday experiences. In the microscopic realm of physics, processes such as particle interactions often appear to be time-symmetric. This means that the fundamental laws governing these particles do not inherently favor a specific direction of time. Yet, the overall tendency of systems to evolve toward higher entropy introduces a universal flow that defines our experience of time's passage. However, when we consider the collective behavior of large numbers of particles, this simple notion of time begins to break down. In the realm of statistical mechanics, as systems evolve, we observe an increase in disorder, a phenomenon that aligns with our everyday perception of time flowing forward. This behavior becomes especially noticeable at larger scales, such as in cosmology. At these vast scales, the arrow of time remains a constant. The expansion of the universe, this evidenced by the redshift observed in distant galaxies, suggests a singular unidirectional evolution of time. As the universe continues to expand and cool, it is transitioning from a hot, dense state to one that is cooler and more dispersed. This transition further emphasizes the irreversible nature of time's passage on a cosmic scale. Interestingly, while time is typically perceived as a linear and unidirectional flow, there are theories within quantum mechanics and general relativity that challenge this basic assumption. Under specific conditions, concepts like time dilation in relativistic physics or quantum entanglement hint at the complexity of time and its flow. These theories suggest that there could be scenarios where our intuitive understanding of time might not apply in the way we expect. Nevertheless, in the macroscopic world and on the scale of the universe itself, time remains a consistent, forward-moving phenomenon. It is deeply tied to the fundamental laws of thermodynamics and the evolution of systems. The principle of causality, that a cause precedes its effect, is a cornerstone of physics. Yet at the quantum level, the behavior of particles and fields introduces intriguing scenarios that challenge our classical understanding of causality. Quantum mechanics operates on principles that, at first glance, seem counterintuitive, leading to interpretations where traditional cause and effect relationships might appear to break down. One of the phenomena sparking debates about causality is quantum entanglement. When two particles become entangled, the state of one particle is instantaneously correlated with the state of another, regardless of how far apart they are. If one particle is measured, the outcome seems to instantly influence the state of the other particle, a phenomenon often called spooky action at a distance. This has led to questions about whether such instantaneous correlations imply a violation of causal order. However, It's crucial to recognize that while entanglement does exhibit non-local correlations, it does not allow for faster-than-light communication or the transmission of usable information. This preserves the essence of causality. The changes in one particle don't influence the other in a manner that could convey information, meaning that the fundamental concept of causality remains intact, even in the quantum realm. Another fascinating aspect of quantum mechanics lies in certain theoretical interpretations, such as those involving time travel or closed time-like curves. These speculative ideas suggest scenarios where the usual flow of cause and effect might be reversed or circumvented entirely. While these propositions invite intriguing exploration into the nature of time and reality, they remain firmly in the realm of theory, as no empirical evidence has yet validated them. Although quantum mechanics presents phenomena that challenge classical ideas of causality, the fundamental principle that causes precede effects largely remains intact. The exploration of quantum causality is a rich field of inquiry, providing deeper insights into the nature of reality and the fundamental workings of the universe. Yet, no concrete examples have yet emerged that definitively violate causality as we understand it. In the extreme environment near a black hole's singularity, time undergoes dramatic changes. As predicted by general relativity, the core of a black hole, the singularity, is a region of infinite density and intense gravitational forces. These forces warp space-time to such an extent that our conventional understanding of both time and space begins to unravel. As one approaches the singularity, time behaves in ways that defy our everyday experiences. For an observer falling into the black hole, time would appear to flow normally at first. However, as they get closer to the event horizon, the point beyond which nothing can escape, the flow of time begins to stretch and distort in ways that would seem completely alien from our perspective on the outside. However, as they approach the event horizon, the boundary surrounding a black hole, beyond which neither matter nor information can escape, the effects of gravitational time dilation become incredibly pronounced. According to Einstein's theory of relativity, time flows more slowly in stronger gravitational fields. To an outside observer, anyone falling into a black hole would appear to slow down, almost freezing in time, their image growing more and more red-shifted as light from them stretches across the spectrum. For the person actually falling into the black hole, their experience would be radically different. They would cross the event horizon without noticing any immediate change. But as they neared the singularity, the point of infinite density at the black hole's core, extreme tidal forces would begin to take hold. These forces could stretch and compress them in what is known as spaghettification, as the laws of physics, as we understand them, break down. At the singularity itself, conventional physics no longer applies. Time, as we perceive it, might lose all meaning. Some theories suggest that time may cease to function altogether in such extreme conditions. In fact, the equations of general relativity fail to offer a clear description of time's behavior under these circumstances, leaving us to question if time itself might become irrelevant in such a state. This breakdown of the conventional flow of time near a black hole's singularity raises profound questions about the very nature of time. While general relativity gives us the framework to explore these phenomena, a deeper, more unified theory that merges general relativity with quantum mechanics might be the key to fully understanding the behavior of time in and around black holes. The study of black holes, still one of the most fascinating frontiers in modern physics, continues to offer potential insights into the fabric of both time and space. One of the greatest and most debated questions in both physics and philosophy is whether time is a fundamental aspect of reality or something that emerges from more basic processes. This distinction is essential. If time is fundamental, it would be a basic building block of the universe, woven into the very fabric of space itself. In classical physics, time is treated as an absolute, unchanging backdrop, a dimension in which events unfold in a consistent, ordered manner. This aligns with the view of time in Newtonian mechanics, where it serves as a steady, fixed reference against which all physical phenomena occur. On the other hand, the emergent view suggests that time might arise from deeper, more fundamental elements, such as quantum processes or particle interactions. Some theorists argue that time could be an emergent property of thermodynamic processes, specifically the increase of entropy as described by the second law of thermodynamics. According to this perspective, the flow of time is the result of statistical behaviors in large systems, rather than being an intrinsic element of reality. In a universe without complex interactions, time as we know it might not even exist. This emergent view also finds support in various approaches to quantum gravity, where space and time may not be fundamental at all. In some models of string theory or loop quantum gravity, time might arise from more primordial, timeless states. In these theories, it's the relationships between particles and the physical dynamics that shape our perception of time. As our understanding of the universe evolves through ongoing research, the question of whether time is fundamental or emergent remains a central puzzle. Both perspectives provoke deep philosophical questions and challenge our very understanding of reality. Unraveling the true nature of time could not only revolutionize our understanding of the universe, but could also reveal groundbreaking insights into the laws that govern it and our place within it. This concept of time behaving differently in different regions of the universe emerges directly from the principles of general relativity and the influence of gravity on the passage of time. According to this theory, time is not uniform across the universe. Instead, it can be affected by gravitational fields and relative velocities, resulting in varying rates of time flow in different regions. One of the most well-known examples of this is gravitational time dilation. As an object approaches a massive body, whether it's a planet, a star, or a black hole, the gravitational field increases, causing time to pass more slowly for that object relative to an observer further away from the massive body. This phenomenon has been verified through numerous experiments, including those with atomic clocks placed at varying altitudes. Clocks closer to Earth's surface, where gravity is stronger, tick slightly slower than those at higher altitudes. Similarly, special relativity tells us that time can be altered by velocity. As an object approaches a significant fraction of the speed of light, time for that object slows down in relation to an observer at rest. This means that if one were to travel at relativistic speeds through space, they would experience time differently than those remaining on Earth. In both cases, time is not the universal absolute concept once imagined. Instead, it is malleable, shaped by gravity and velocity, leading us to reconsider everything we know about the nature of time itself. Moreover, theoretical models, including those that explore wormholes and cosmic strings, suggest the possibility of regions in space where our conventional understanding of time might not just stretch, but collapse entirely. In these extraordinary structures, the very fabric of space-time could be distorted in ways that allow for interactions with time that are entirely unconventional, possibly enabling time travel or creating zones where time behaves in fundamentally different manners. These concepts, though deeply rooted in theoretical frameworks, open up a fascinating realm of possibilities. They underscore a profound truth. Time is intricately woven into the very structure of the universe, tethered to the forces that govern it. As our knowledge of physics expands, particularly in the realms of quantum gravity and cosmology, the idea of regions where time behaves differently becomes an exciting frontier of discovery. Every breakthrough in this field promises to shed light on new dimensions of how time interacts with the cosmos, offering glimpses of a universe where the passage of time is not as fixed as we once thought. This ongoing evolution of thought has the potential to reveal answers to some of the most profound questions we've ever asked about the universe. At the heart of this cosmic story lie supermassive black holes. These enigmatic giants, which can possess millions or even billions of times the mass of our sun, are pivotal players in the evolution of galaxies. Often found at the centers of large galaxies, including our own Milky Way, supermassive black holes wield an influence that stretches far beyond their immediate surroundings. Their gravitational pull affects not only the stars and gas within the galaxy, but the very shape and dynamics of galactic structures themselves. The gravitational force of these massive objects can drive profound changes in the galaxy's composition. Stars and gas are guided into distinct patterns, forming dense stellar bulges at the galactic core. These interactions influence the long-term stability of the galaxy and determine how it will evolve. As if by cosmic design, supermassive black holes are not just passive objects, they are active forces shaping the destiny of galaxies. When matter falls into these black holes, it forms an accretion disk, heating up and emitting radiation across various wavelengths, including X-rays and radio waves. This intense energy output has far-reaching consequences, regulating the star formation within the galaxy. During periods of high accretion, the energetic outflows can heat surrounding gas to such an extent that it is expelled from the galaxy entirely, suppressing further star formation. This feedback loop acts as a kind of cosmic thermostat, preventing the galaxy from overproducing stars and directing its evolutionary path toward a balanced state. Additionally, supermassive black holes play a crucial role during galaxy mergers. When galaxies collide and merge, their supermassive black holes exert a powerful gravitational influence, guiding gas towards the centers of the newly formed galaxies. This can trigger bursts of star formation as the gas concentrates, and in the process, the black holes themselves may grow larger. The dynamic interplay between merging galaxies and their black holes creates a feedback loop that drives the ongoing evolution of galactic structures on a cosmic scale. Supermassive black holes are therefore not only catalysts for the formation and transformation of galaxies, but also key participants in the cosmic dance that shapes the larger universe. As astronomers continue to study these objects, new insights are emerging about their complex relationship with the galaxies they inhabit. This ongoing research enhances our understanding of the universe's intricate design, offering a glimpse into the processes that govern its growth. The cessation of star formation in certain galaxies is another fascinating aspect of galactic evolution. Several interconnected processes contribute to this phenomenon, with one of the most significant being the depletion of gas, the fundamental raw material for creating new stars. When a galaxy runs out of cold gas, often due to extensive star formation or violent outflows driven by supernovae and stellar winds, it loses its ability to generate new stars. Once the supply of gas dwindles, the galaxy enters a dormant, passive state, effectively halting its star-forming activity. Supermassive black holes further contribute to this shift. When these colossal objects are actively consuming matter, they can produce powerful jets and outflows that inject vast amounts of energy into the surrounding interstellar medium. This energetic feedback prevents the gas from cooling and collapsing to form new stars, thereby suppressing future star formation. Moreover, galaxy mergers often provide a temporary burst of star formation, but the aftermath can be equally transformative. The gravitational interactions between merging galaxies can lead to the expulsion or heating of gas, further stifling star creation. In densely populated environments, such as galaxy clusters, external factors also come into play. Ram pressure stripping, for instance, occurs when a galaxy moves through the hot cluster medium, stripping away its surrounding gas. This rapid removal of gas can swiftly halt any remaining star formation. Thus, the fate of star formation in a galaxy is shaped not only by internal dynamics, but also by the larger environment in which it exists. The interplay between gas depletion, black hole activity, and external pressures from the cosmic surroundings sets the stage for the evolutionary trajectory of galaxies across the universe. These complex processes demonstrate the delicate balance that governs the formation and destruction of stars, painting a picture of a universe that is continually changing and evolving. Galaxies are dynamic and ever-evolving systems, influenced by numerous factors that shape their behavior and characteristics over time. One of the most significant of these is the gravitational interaction with neighboring galaxies. These cosmic interactions can generate tidal forces that disrupt the gas reservoirs essential for star formation. Over the vast stretches of cosmic time, such disruptions contribute to the wide variety of galaxy types we observe today, from the intense, star-forming starburst galaxies to the more tranquil, elliptical galaxies that exhibit little to no ongoing star formation. Understanding the mechanisms that halt star formation allows astronomers to piece together the complex puzzle of galaxy evolution, providing insight into the broader cosmic processes that govern the life cycle of galaxies. Each new discovery in this field brings us a step closer to understanding the intricate relationships between galaxies, their environments, and the universe itself. Galaxies are not isolated entities. They are deeply connected to their surroundings, constantly interacting with the intergalactic medium. These interactions allow for the exchange of matter through several processes which are fundamental to a galaxy's growth and evolution. One of the most striking of these processes is the phenomenon of galactic winds. Driven by stellar winds and the catastrophic explosions of supernovae, galactic winds are powerful outflows of gas. When massive stars end their life cycles in supernova events, they release immense amounts of energy and material into the surrounding space. This energy propels gas and dust out of the galaxy, carrying with it the heavy elements that were synthesized in the stars. Some of this ejected material may later be reaccreted by other galaxies, contributing to their own growth and evolution. In addition to losing material, galaxies can also gain matter through a process known as gas accretion. This is the act of drawing in primordial hydrogen and helium, the building blocks of the universe. This inflow of gas acts as a fuel source for star formation, ensuring that galaxies continue to grow and evolve. Through this exchange of gas and energy, galaxies can replenish the materials lost during stellar processes and maintain their capacity to form new stars. But the relationship between galaxies is not always so straightforward. Galactic mergers add another layer of complexity to this already dynamic process. When two galaxies collide, their interstellar gas clouds merge, often resulting in a burst of star formation, known as a starburst. During this event, the gravitational forces from the collision cause gas from both galaxies to flow into the intergalactic medium, enriching it with matter while also disrupting the galaxy's structures. This interaction not only facilitates the exchange of material, but also dramatically influences the merging galaxy's evolution, leading to significant changes in their shape and composition. Starbursts are intense periods of star formation that can drastically alter a galaxy's structure and future development. These bursts are usually triggered by various cosmic events, with gravitational interactions playing a key role. When galaxies come into close proximity or collide, the gravitational forces involved can compress their gas and dust. This compression triggers a surge in star formation, creating new stars at a much faster rate than would normally occur. Another powerful driver of starbursts is the influence of a galaxy's environment. In regions of space where galaxies are densely packed, such as in galaxy clusters, galaxies can experience ram pressure stripping. This phenomenon occurs when the intergalactic medium exerts pressure on the gas of a galaxy, stripping away its outer gas layers. When this happens, the remaining gas becomes more concentrated. As this concentrated gas collapses, it can trigger accelerated star formation, leading to another burst of stellar activity. These various processes, gravitational interactions, galactic winds, gas accretion, and galactic mergers, work together to create the diverse range of galaxies that populate our universe. Understanding these intricate interactions is key to unlocking the secrets of galaxy formation, evolution, and the very life cycle of galaxies themselves. Each discovery in this field contributes to our growing understanding of the cosmos and the complex web of relationships that bind galaxies together. Internal processes are key players in triggering starbursts, dramatic events where new stars are formed in bursts of activity. The creation of new stars is often fueled by the accumulation of gas that flows into a galaxy's central regions. A powerful force behind this accumulation is feedback from existing stars and supernovae. These cosmic explosions release intense energy that heats and redistributes the surrounding gas, making it more prone to collapse under its own gravity and eventually forming new stars. This self-regulating cycle, which happens in galaxies across the universe, can result in explosive periods of star formation, known as starbursts, when conditions align just right. Starbursts can also occur in response to major cosmic events in a galaxy's evolution, such as the influx of gas from the intergalactic medium or following the merger of two galaxies. These dramatic events introduce fresh gas into the galaxy, sparking renewed star formation. But unlike regular steady star formation, starbursts are brief but explosive. During these outbursts, a significant portion of the galaxy's gas is converted into new stars, permanently altering the galaxy's future evolution. In addition to the dynamics of star formation, galactic magnetic fields offer another fascinating layer of complexity. These fields arise from a mix of factors, primarily involving the movement of electrically charged particles and the dynamics of the galaxy itself. It's believed that magnetic fields in galaxies originate from the motions of ionized gases combined with the galaxy's rotation. As gas and stars within a galaxy rotate and interact, they stir up turbulence and vortices that generate electric currents. These currents, in turn, give rise to magnetic fields. At first, these fields may be weak and chaotic, but as the gas continues to move and interact, the fields become stronger, more organized, and more structured. The formation of magnetic fields in galaxies is driven by what's known as the dynamo effect. When a conducting fluid like ionized gas moves through a magnetic field, it induces electric currents, which then amplify the field. Over time, these magnetic fields evolve as the galaxy itself evolves. The rotation of the galaxy, along with the flow of gas, often shapes these magnetic fields into radial or spiral structures. When galaxies merge, their magnetic fields can be distorted and amplified, producing intricate patterns that influence the overall behavior of the galaxy. These complex magnetic configurations can, in turn, affect the rate of star formation and alter the dynamics of the galaxy. Additionally, the evolution of magnetic fields is influenced by cosmic events such as supernova explosions. When massive stars explode in a supernova, they not only release vast amounts of energy, but also inject magnetic material back into the interstellar medium. This magnetic material interacts with pre-existing fields, contributing to their growth and complexity. As the cycle of star formation, magnetic field generation, and cosmic events continues, the study of galactic magnetic fields remains a central focus of modern astrophysics, offering valuable insights into the nature of galaxies and their ongoing evolution. Now, consider the diverse shapes that galaxies take on, from spiral and elliptical to irregular forms. These shapes are not only the result of the galaxy's initial conditions, but are also profoundly influenced by their formation history, their interactions with other galaxies, and the dynamics of their stars and gas. A galaxy's shape is largely dictated by how it formed. For example, galaxies born from more uniform gas tend to develop spiral structures, with well-defined arms of young stars and nebulae. In contrast, galaxies formed from more chaotic conditions may evolve into elliptical galaxies, marked by smooth, featureless profiles. But formation is just one piece of the puzzle. Interactions between galaxies can drastically alter their morphology. When two galaxies collide, their gravitational forces distort their shapes and can trigger intense bursts of star formation. This merging process can result in various outcomes, such as the formation of irregular galaxies that lack a clear structure, or the transformation of spiral galaxies into elliptical ones. In these cases, the redistribution of gas and stars within the galaxy creates a complex internal structure, reflecting the turbulent history that shaped it. A galaxy's environment also plays a significant role in determining its shape. In denser regions of the universe, such as galaxy clusters, gravitational interactions occur more frequently, which leads to higher rates of mergers and transformations. In these crowded environments, galaxies can lose their gas through a process known as ram pressure stripping, which prevents them from forming new stars and can alter their structure, often transforming their once dynamic shapes into more passive ones. On the other hand, galaxies located in less dense regions are more likely to retain their gas, which helps preserve their spiral structure and supports ongoing star formation. These intricate processes, feedback mechanisms driving star formation, the evolution of galactic magnetic fields, and the complex interplay between galaxies and their environments demonstrate the dynamic and ever-changing nature of galaxies. Each one is a living, breathing entity, constantly evolving in response to both internal and external forces. Studying these processes not only enriches our understanding of galaxies, but also provides a window into the broader workings of the universe. Dark matter plays a crucial and often mysterious role in the universe, shaping the cosmos in ways we are still striving to fully comprehend. Its gravitational pull, which is responsible for a significant portion of the universe's mass, stabilizes and organizes galaxies, creating a web of structures across space. The distribution and properties of dark matter halos surrounding galaxies have profound effects on their dynamical evolution. These halos influence the rate at which stars are born, and they are key factors in determining the shapes and sizes of galaxies over time. The intricate balance between dark matter's pull and the visible matter within galaxies leads to the stunning diversity of galaxy morphologies that we observe in the vast expanse of the universe. In this grand cosmic dance, one of the most enigmatic forces is the Great Attractor, a massive gravitational anomaly located in the direction of the Centaurus and Hydra constellations, roughly 200 million light years from Earth. This peculiar region is home to a dense concentration of mass that exerts a powerful gravitational influence on the surrounding galaxies, particularly those in our local supercluster, the Laniakea supercluster. The Great Attractor's gravitational force pulls galaxies toward it, causing them to move in peculiar ways that deviate from the general expansion of the universe. At the heart of this gravitational powerhouse lies a large galaxy cluster, including a particularly massive component known as the Norma cluster. Yet the true intrigue of the Great Attractor lies not only in its immense gravitational pull, but also in the challenge it presents to astronomers. The region is obscured by the Milky Way's galactic plane, making it incredibly difficult to observe directly. This obstruction limits our ability to study its exact composition and structure in detail. Nevertheless, the gravitational effects of the Great Attractor are unmistakable. The influence of this vast mass ripples through space, affecting the motion of countless galaxies, including our own. Galaxies in the vicinity are drawn toward this region, contributing to the phenomenon known as the flow of galaxies. Observations indicate that our own galaxy, the Milky Way, along with other members of the local group, is moving toward the Great Attractor at significant velocities. Ongoing research into this gravitational anomaly continues to shed light on the large-scale structure of the universe. It serves as a reminder that even unseen masses can exert a profound influence on the visible universe, orchestrating the motion of galaxies in ways that are both subtle and dramatic. The Great Attractor illustrates how interconnected and dynamic cosmic structures are as they navigate the ever-expanding fabric of the universe. Another fascinating cosmic feature that has intrigued scientists for years is the cold spot in the cosmic microwave background radiation, CMB, a phenomenon that continues to inspire deep exploration. This cold spot represents an area in the remnant radiation from the Big Bang that is significantly colder than the surrounding regions of the universe. The CMB acts as a snapshot of the early universe, offering invaluable insights into its origins, structure, and subsequent evolution. One leading explanation for the cold spot involves fluctuations in the density of matter shortly after the Big Bang. As the universe expanded, small quantum fluctuations in density led to the formation of clusters of matter and vast voids. The cold spot may correspond to such a cosmic void, an underdense region of space where fewer galaxies and less matter are located. The lack of matter in this region would result in lower radiation emission, causing the temperature to be cooler in that specific area of the CMB. An alternative hypothesis suggests that the cold spot could be the result of gravitational lensing, where light from the early universe is distorted as it travels through massive structures such as galaxy clusters. In this scenario, the cold spot would not be the result of an underdense region, but rather the effect of massive objects bending light and altering the perceived temperature of the CMB. Some researchers have even proposed more radical theories, suggesting that the cold spot could be evidence of new physics beyond the current cosmological model. While these ideas remain speculative and are still under investigation, they underscore the intriguing nature of the cold spot and fuel curiosity about the potential for discoveries that could alter our understanding of the universe's structure and history. Ultimately, the cold spot and its possible explanations serve as an invitation for scientists to probe deeper into the mysteries of the cosmos. It is a phenomenon that not only challenges our understanding of the universe's early history, but also hints at the complex, often unseen forces that govern the cosmos. Whether the cold spot is simply an artifact of cosmic voids, a result of gravitational lensing, or a sign of more exotic physics at play, it remains a focal point for ongoing research and a testament to the mysteries that still await discovery in the vast, expanding universe. The existence of this cold spot in the cosmos deepens our understanding of cosmic history, sparking ongoing inquiries into the fundamental properties of the universe itself. One of the most fascinating phenomena linked to this discovery is the alignment of quasar polarizations across vast cosmic distances. This intriguing occurrence raises profound questions about the structure of the universe, the behavior of light, and the forces that shape both. Quasars, or quasi-stellar objects, are intensely luminous active galactic nuclei powered by supermassive black holes. These black holes emit enormous amounts of radiation, and as this radiation travels through intergalactic space, it can become polarized. Polarization describes the orientation of light waves, which can reveal critical information about the medium through which the light travels. Several factors contribute to the alignment of quasar polarizations. A primary influence is the intergalactic medium itself, which often contains magnetic fields that can impact the way light propagates. When light from a quasar passes through these magnetic fields, interactions occur that can induce polarization, aligning the light waves in certain directions. If these magnetic fields are coherent over large scales, they can produce a consistent alignment of quasar polarizations across vast distances. Another critical element is gravitational lensing, caused by massive foreground objects like galaxy clusters that lie between the quasar and Earth. As light from a quasar bends around these enormous cosmic bodies, the resulting light paths may form polarization patterns that reflect the gravitational influence exerted by these objects. This lensing effect can reinforce the alignment of polarization angles, especially if multiple quasars are affected by similar gravitational fields, further emphasizing the interconnected nature of cosmic structures. In addition to these external influences, the intrinsic properties of quasars themselves also play a role in polarization alignment. Some quasars feature relativistic jets, streams of high-energy particles ejected from the poles of the supermassive black hole. These jets can inherently emit polarized light. If multiple quasars exhibit similarly oriented jets, this could contribute to the observed polarization patterns, creating a unifying thread that links quasars over vast expanses of space. The alignment of quasar polarizations invites further exploration into the mechanisms that govern the universe's large-scale structure. By carefully analyzing these polarization patterns, scientists can uncover insights into the cosmic web, the intricate network of galaxies, dark matter, and intergalactic gas. This also allows for a deeper understanding of how light behaves across immense distances and how matter and radiation interact in the most distant reaches of space. Another puzzle that has long fascinated astronomers is the appearance of certain galaxies as being older than the universe itself. This enigma stems from a combination of factors tied to cosmic evolution, the limitations of observational techniques, and the methods used to estimate a galaxy's age. One of the most influential contributors to this paradox is the phenomenon of redshift. When light from distant galaxies reaches us, it is often redshifted due to the expansion of the universe. This redshift indicates that the light was emitted at a much earlier time, and the greater the redshift, the further back in time we are observing. In some cases, astronomers examine galaxies at high redshifts where the light has taken an extraordinary amount of time to reach Earth. Because we are observing the galaxy as it was when the universe was younger, it can give the impression that the galaxy itself is older. This phenomenon creates the illusion that some galaxies formed shortly after the Big Bang and have since remained relatively unchanged. As a result, estimates of their ages may exceed the actual age of the universe, leading to apparent discrepancies in our understanding of cosmic timelines. The methods used to determine a galaxy's age also play a significant role in this confusion. Astronomers often rely on the properties of the stars within these galaxies, specifically their stellar populations and the presence of evolved older stars, to estimate their age. If a galaxy has a significant population of older stars, it can be classified as older than initially expected. However, this approach can be misleading, especially if the galaxy's star formation activity has slowed down, giving the impression of an ancient stellar population. Thus, the age of a galaxy, as determined through current astronomical techniques, is a complex calculation, one that can sometimes lead to conclusions that appear to defy our understanding of the cosmos. These cosmic mysteries highlight the complexities of studying the universe's past and the challenges of measuring the true age of galaxies scattered across the vast expanse of space. Through these enigmatic phenomena, the polarization of quasars and the apparent age of certain galaxies, scientists are continuously refining their tools and methods, striving to unlock the secrets of the cosmos and better understand the forces that shape the universe over billions of years. However, these estimates can vary greatly depending on the models used and the assumptions made about star formation rates and stellar evolution, which often leads to discrepancies in age estimates. Another intriguing possibility lies in the existence of fossil galaxies, a concept that suggests certain galaxies may have formed incredibly early in the universe's history. These ancient galaxies could have experienced rapid star formation, evolving quickly before the universe was fully structured. As a result, the characteristics of these galaxies might indicate ages that appear to surpass the age of the universe itself. Understanding the complex relationships behind these discrepancies is crucial for refining our models of galaxy formation and evolution. It is also essential for reconciling observations with our current cosmological framework. As more data is gathered and analyzed, scientists continue to gain deeper insights into the age and nature of galaxies, which in turn enriches our understanding of the universe's vast history. The Fermi paradox presents a puzzling conundrum. Given the vast number of stars and potentially habitable planets scattered across the universe, why have we not encountered any signs of extraterrestrial life? Named after the physicist Enrico Fermi, this paradox highlights the contradiction between the high probability estimates of extraterrestrial civilizations and the complete lack of evidence or contact with them. One potential explanation for the Fermi paradox lies in the sheer scale and age of the universe. With billions of galaxies, each containing millions to billions of stars, it's likely that countless planets could support life. However, the distances between these stars and their planets are truly immense. The vastness of space, combined with the finite speed of light, means that even if intelligent civilizations exist relatively close by, the time it would take for their signals to reach us makes contact extremely unlikely within the span of a human lifetime. Another factor to consider is the development and sustainability of intelligent life itself. While simple life forms may be common in the universe, the emergence of complex, intelligent civilizations could be an exceptionally rare occurrence. This rarity could be the result of numerous factors, such as the specific conditions required for life to evolve, extinction events that wipe out emerging civilizations, or technological and societal challenges that prevent civilizations from enduring long enough to make contact with other worlds. In some cases, civilizations might self-destruct due to war, ecological collapse, or technological disasters before they can develop the means to communicate or venture beyond their own star systems. Furthermore, the behavior of advanced civilizations might also be a contributing factor. If intelligent life does exist, it's possible that such civilizations may choose to remain isolated, deliberately avoiding communication with others. They may possess technologies beyond our detection capabilities, or simply have no desire to interact with less advanced civilizations. Some theorists suggest that we may be in the midst of a great filter scenario, where civilizations face overwhelming challenges that limit their capacity to reach a stage where they can communicate or expand beyond their solar systems. Ultimately, the Fermi paradox continues to inspire deep discussions in the fields of astrobiology and cosmology. It raises fundamental questions about the development of life, the evolution of technology, and humanity's place within the vast expanse of the universe. As researchers continue to explore the cosmos with increasingly advanced telescopes and missions, the search for extraterrestrial life remains one of humanity's most compelling quests, one that could redefine our understanding of intelligence and life itself. The observed shortage of lithium-7 in the universe is another intriguing puzzle in cosmology and nucleosynthesis. According to the Big Bang theory, various light elements, including hydrogen, helium, and lithium, were created during the first few minutes after the Big Bang in a process known as Big Bang nucleosynthesis. Yet, when we examine the actual abundance of lithium-7 in the universe, it falls significantly short of the theoretical predictions. Several factors contribute to this discrepancy, with one prominent explanation tied to the processes that take place during the formation and evolution of stars. When stars are born, they primarily consume hydrogen and helium, and through the process of nuclear fusion, they can alter the relative abundances of light elements. In particular, stars can destroy lithium during their fusion processes. As stars age and undergo stellar nucleosynthesis, any lithium present can be depleted, especially in higher mass stars that burn fuel more quickly and reach higher temperatures. Stellar outflows and winds, the dynamic forces that govern how stars shed mass, play a crucial role in shaping the composition of the universe. As stars undergo these processes, they can expel freshly synthesized material into the interstellar medium, enriching the cosmic environment. However, this expulsion often comes at a cost. One of the elements most affected by these high-energy stellar environments is lithium-7. Under the intense conditions within stellar interiors or during supernova explosions, lithium-7 can be photodissociated, meaning it is broken down by high-energy photons, or it can be transformed into heavier elements, leading to a net loss of this light element. Additionally, the cosmic ray spallation process offers another key piece of the puzzle when it comes to understanding lithium-7's abundance. Cosmic rays, high-energy particles traveling through space, can collide with heavier elements, triggering nuclear reactions that produce lighter elements, including lithium. While this process does generate lithium, it is unlikely to create enough lithium-7 to fully explain its observed deficit in the universe. The mysteries deepening around lithium-7 are also linked to the initial conditions of the universe itself. The assumptions we make about the density of baryonic matter and the expansion rate of the universe can dramatically influence the predicted abundances of light elements, such as lithium-7. Variations in these parameters during the Big Bang could lead to a lower than expected yield of lithium-7, contributing to the ongoing enigma. In this way, the shortage of lithium-7 represents a fascinating intersection of stellar evolution, nucleosynthesis, and cosmic conditions. This discrepancy continues to inspire researchers around the world to refine theoretical models, gather observational data, and seek explanations that bridge the gap between theory and observation. Each discovery brings us one step closer to a deeper understanding of the processes that have shaped the elements in our universe. Beyond the realm of stellar physics, there are compelling reasons to believe that particles beyond the standard model of particle physics may exist. While the standard model has proven remarkably successful in explaining a wide range of phenomena and the fundamental particles that constitute our universe, it is far from complete. It accounts for 3 of the 4 fundamental forces: electromagnetic, weak, and strong interactions. However, it leaves out some crucial aspects of the cosmos, opening the door to potential new particles that could extend beyond its current framework. One of the most pressing areas where the standard model falls short is in its inability to explain the nature of dark matter. Observations of galaxies and galaxy clusters show that the majority of matter in the universe is invisible. Dark matter does not emit, absorb, or reflect electromagnetic radiation, making it undetectable by conventional means. Yet, its gravitational effects on visible matter are undeniable. This has led scientists to propose that dark matter may be composed of yet unidentified particles, such as weakly interacting massive particles, or WIMPs. These particles would interact very weakly with normal matter, making them incredibly difficult to detect. However, their presence could help explain many of the unexplained phenomena observed in the cosmos. Another area where new particles might extend our understanding is in the quest to unify all fundamental forces, including gravity. While the standard model successfully describes the electromagnetic, weak, and strong forces, gravity does not fit neatly within this framework. Theories such as string theory and quantum gravity propose that additional particles, like gravitons, may exist. Gravitons are hypothetical particles that mediate the force of gravity, much like how photons mediate electromagnetic forces. However, gravity's current inability to be integrated into the standard model suggests that new particles or concepts are needed to bridge this gap. Moreover, the discovery of neutrino oscillations, the phenomenon in which neutrinos change flavor as they travel, has revealed that neutrinos have mass, a property that the standard model does not account for. This surprising finding has spurred physicists to explore the possibility of additional particles or mechanisms that could help explain this phenomenon. Right-handed neutrinos or Majorana fermions are among the candidates being investigated as potential explanations, pointing to the fact that the Standard Model may only represent a fraction of the true complexity of the universe. The exploration of these questions offers a thrilling glimpse into the unknown, pushing the boundaries of our understanding of the universe's most fundamental aspects. As scientists continue their search for new particles and phenomena beyond the Standard Model, we inch closer to uncovering the deeper truths that govern the cosmos. The search for new particles and potential physics beyond the Standard Model is one of the most exciting frontiers in modern science. Experiments at facilities like the Large Hadron Collider, LHC, are at the forefront of this search, actively looking for signs of new physics. These experiments aim to uncover clues about supersymmetric particles, extra dimensions, and other unknown aspects of the universe's fundamental laws. The ongoing research into these phenomena holds the thrilling possibility of transforming our understanding of how the universe works at its most fundamental level. Among the most captivating phenomena in particle physics is the oscillation of neutrinos. Neutrinos, which are incredibly elusive and difficult to detect, have puzzled scientists for decades. They are produced in various processes, including nuclear reactions in the sun, cosmic ray interactions, and radioactive decay. What makes neutrino oscillations especially intriguing is that these particles are not static. They can change their flavor as they travel through space. Neutrinos exist in three distinct flavors: electron neutrinos, muon neutrinos, and tau neutrinos. Each flavor corresponds to a specific charged lepton, electron, muon, and tau, respectively. However, neutrinos are not just simple, massless particles. It turns out that they have a small but measurable mass, which is a key component of the oscillation phenomenon. These mass differences cause neutrinos to travel at different speeds, which leads to the oscillation effect as they move through space. The oscillation occurs because the three neutrino flavors do not have the same mass. When a neutrino is created, it is actually a mixture of all three flavors, each with a certain amplitude. As the neutrino travels, the components of this mixture evolve differently, causing the probabilities of detecting it as one flavor or another to change over time. This behavior, deeply tied to quantum mechanics and the principle of superposition, means that neutrinos constantly change their identity, exhibiting the oscillation effect. The discovery of neutrino oscillations has had profound implications. It provided strong evidence that neutrinos have mass, challenging the original assumptions of the Standard Model, which held that neutrinos were massless. This breakthrough has led to new areas of research, such as the exploration of additional types of neutrinos, the seesaw mechanism, and potential interactions with other unknown particles. The study of neutrino oscillations is crucial for answering some of the most fundamental questions about the universe, such as the nature of matter and antimatter, as well as the evolution of the cosmos itself. As experiments continue at various facilities, our understanding of these mysterious particles grows, offering new insights into the very nature of the universe. In a similar vein, magnetic monopoles, hypothetical particles that would carry a net magnetic charge, have intrigued scientists for years. Unlike electric charge, which exists as positive or negative in particles like electrons and protons, magnetic charge has never been observed in isolation. Magnetic fields are typically formed by dipoles with both a north and a south pole. However, the idea of a magnetic monopole, one that would have only a single magnetic pole, raises profound questions about the fundamental nature of magnetism and the forces that govern the universe. The theoretical foundations for magnetic monopoles were laid early in the 20th century by physicists like Paul Dirac. He proposed that the existence of magnetic monopoles could explain the quantization of electric charge, a mystery that had puzzled scientists for some time. Despite these theoretical predictions, direct experimental evidence for magnetic monopoles has yet to be found. Various searches have been conducted, particularly in high-energy physics experiments and cosmic ray studies, but no clear detection has confirmed their existence. Nevertheless, the quest for magnetic monopoles continues, as their discovery could have profound implications for our understanding of magnetism and the unification of forces. Whether or not they are eventually found, the search itself reflects the ongoing efforts to push the boundaries of what we know about the universe. The pursuit of such unknowns, from neutrinos to magnetic monopoles, is a testament to the relentless curiosity and determination of scientists to explore the very building blocks of nature. However, despite significant progress, certain anomalies in experimental data and lingering gaps in our physical theories continue to point toward the intriguing possibility of magnetic monopoles. These hypothetical particles, magnetic equivalents of electric charges, could exist under specific conditions, particularly within the realms of quantum field theory or the pursuit of grand unified theories, GUTS. GUTS aim to merge the three fundamental forces of nature: the electromagnetic, weak, and strong forces. While direct evidence of magnetic monopoles remains elusive, researchers have also turned to condensed matter physics, where phenomena resembling monopole behavior have been observed. For instance, in spin ice systems, materials that exhibit complex magnetic properties, magnetic monopole-like excitations have been detected. These phenomena offer promising insights into the topological properties of magnetic fields, suggesting that even if magnetic monopoles do not exist in the traditional sense, their mathematical and physical characteristics could still shape our understanding of the universe's magnetic landscape. The possibility of magnetic monopoles continues to capture the imagination of physicists. Their discovery would not only represent a groundbreaking achievement in particle physics, but also potentially unlock new dimensions of knowledge about fundamental forces, including those governing the origins of the universe itself. Despite their tantalizing nature, the existence of magnetic monopoles remains unproven, leaving them as a frontier of ongoing theoretical and experimental research in physics. Whether in the laboratory or through advanced cosmic observations, the search for monopoles may one day redefine our understanding of magnetic phenomena, deepening our comprehension of the universe's most fundamental aspects. The origin of matter-antimatter asymmetry, an apparent imbalance between matter and antimatter, remains one of the most profound mysteries in modern cosmology and particle physics. According to the prevailing theories, the Big Bang should have produced equal amounts of both, given the symmetry of the fundamental laws governing their creation. Yet observational evidence shows that the universe is overwhelmingly composed of matter, with only trace amounts of antimatter detectable. This discrepancy challenges our most basic assumptions about the universe's origins and evolution. One of the leading explanations for this imbalance is the theory of baryogenesis, which proposes that during the early moments of the universe, certain processes favored the creation of baryons, particles such as protons and neutrons, over their antimatter counterparts. Several conditions have been suggested that might have led to this baryon asymmetry, all of which align with criteria set out by Russian physicist Andrei Sakharov in the 1960s. These conditions involve the violation of fundamental symmetries: baryon number conservation, charge conjugation symmetry, C symmetry, and CP symmetry, which is the combination of charge conjugation and parity symmetry. The violation of these symmetries would have enabled the laws of physics to treat matter and antimatter differently, thus tipping the scale in favor of matter during the cooling of the universe. Among the most significant interactions that may have contributed to this imbalance are those occurring within the weak nuclear force. These interactions are known to violate CP symmetry, which could have played a crucial role in generating an excess of baryons as the universe cooled following the Big Bang. The exact mechanisms, however, remain uncertain. Moreover, cosmological scenarios like the electroweak phase transition, which may have occurred as the universe cooled from extremely high temperatures, are also under intense scrutiny. If the conditions during this period had been right, they could have triggered further processes that produced a surplus of baryons. In addition, models that incorporate hypothetical particles, such as those predicted by grand unified theories, GTEATs, or supersymmetry, SUSE, also offer potential explanations for the matter-antimatter asymmetry. These theories suggest that new symmetries or interactions not yet observed may have played a role in this cosmic imbalance. Despite decades of research, the exact origin of the matter-antimatter asymmetry remains an open question, prompting continuous investigation in both theoretical and experimental physics. Researchers are leveraging cutting-edge particle accelerators as well as astronomical observations to gather data that might finally shed light on this fundamental enigma. Understanding why the universe is dominated by matter rather than an equal mixture of matter and antimatter could profoundly alter our view of the cosmos. The search for undiscovered symmetries in particle physics represents another exciting frontier in modern science. Symmetries lie at the core of physical laws, dictating the conservation of certain quantities and helping guide the development of theoretical frameworks. While the standard model of particle physics has been successful in describing many fundamental interactions through well-known symmetries, such as gauge symmetry and Lorentz symmetry, it is increasingly clear that these may not be the whole story. There are several motivations for exploring deeper, yet undiscovered symmetries. One primary reason stems from the limitations of the standard model itself, which does not incorporate gravity and fails to explain phenomena like dark matter and dark energy, two mysterious components that together make up the majority of the universe's energy content. As a result, theories such as string theory and grand unified theories, GTTs, have emerged, suggesting that the fundamental forces of nature could be unified under a single framework. These theories propose the existence of additional symmetries, potentially leading to the discovery of new particles or interactions that could revolutionize our understanding of the universe. While the standard model has provided an incredibly successful description of particle physics, it is likely that deeper layers of symmetry await discovery. Symmetries that could unify the fundamental forces, explain dark matter and dark energy, and perhaps even offer a glimpse into the mysterious origins of the universe itself. This quest for new symmetries is far from academic. It could fundamentally reshape our understanding of the forces that govern the universe and our place within it. Moreover, some researchers are exploring the possibility of symmetries tied to additional dimensions within the framework of string theory and related theories. There is a compelling suggestion that the universe may possess more spatial dimensions than the three we experience daily. These extra dimensions could be associated with unique symmetries, which may give rise to new physical phenomena still waiting to be discovered. Another critical area of focus revolves around the relationship between particles, particularly the potential symmetries between matter and antimatter. This research could provide valuable insights into the puzzling matter-antimatter asymmetry observed throughout the universe. If such symmetries were uncovered, it could reveal the mechanisms responsible for the overwhelming presence of matter and the scarcity of antimatter in our universe. Researchers are also delving into the implications of supersymmetry, an extension of the standard model of particle physics. Supersymmetry proposes a symmetry between fermions, the building blocks of matter, and bosons, the force carriers. Although no direct evidence for supersymmetry has been found yet, its discovery could point to even more profound symmetries within the particle world, unlocking new avenues for understanding the universe's fundamental workings. As experimental methods continue to advance, particularly with tools like the Large Hadron Collider, LHC, and emerging observational technologies, the search for undiscovered symmetries is sparking fresh theories and experimental approaches. Every new symmetry uncovered has the potential to reshape our perception of the universe's fundamental components, unveiling a more intricate and dynamic tapestry of physics lying just beyond our current knowledge. At the highest energies, matter behaves in ways that push the limits of our understanding. These extreme conditions are found in environments such as high-energy particle collisions at facilities like the LHC, or in cosmic events like supernovae and gamma-ray bursts. As energy levels rise, the interactions between particles become increasingly complex, often giving rise to phenomena that challenge the core principles of the standard model of particle physics. One of the most intriguing possibilities arises when particles collide with energies approaching the Planck scale, approximately 10 to the power of 28 electron volts. At this energy scale, it is theorized that gravity could become comparable in strength to the other fundamental forces, electromagnetic, weak, and strong, potentially leading to the unification of these forces. Such conditions might also lead to the creation of miniature black holes or trigger processes linked to quantum gravitational effects, phenomena that remain unobserved to this day. At these extreme energy levels, particles may also undergo pair production, a process in which energy is converted into mass, creating particle-antiparticle pairs. This phenomenon suggests that under the right conditions, a high-energy photon could create a particle and its corresponding antiparticle. For instance, when protons collide at sufficiently high energy, they can generate heavy quarks or even more exotic particles, expanding the known particle zoo far beyond what is commonly seen under normal circumstances. Additionally, quantum chromodynamics, QCD, the theory describing the strong interaction, plays a crucial role at high energy levels. When quarks and gluons are subjected to these extreme conditions, their behavior can differ significantly from that observed in standard environments. This could lead to the formation of a quark-gluon plasma, a state of matter where quarks and gluons are no longer confined within individual protons and neutrons, but instead behave as a fluid. This form of matter is thought to have existed immediately following the Big Bang and remains a central focus of research in heavy ion collision experiments. As we delve deeper into these high-energy realms, scientists are uncovering new physics that extends beyond the standard model. These discoveries may help illuminate the fundamental properties of matter and the forces that govern the interactions between these building blocks of the universe. The exploration of matter at such extreme energies continues to be one of the most exciting and active areas of research, providing critical insights that could ultimately reshape our understanding of the cosmos. The cosmological constant stands as one of the cornerstones in our understanding of the universe, yet its true nature remains elusive. First introduced by Albert Einstein within the framework of his general theory of relativity, the cosmological constant is a measure of the energy density embedded in empty space, what we call vacuum energy. This concept is crucial for explaining the accelerated expansion of the universe, a phenomenon that has intrigued scientists for decades. However, despite its significance, the precise value of the cosmological constant remains one of the most perplexing questions in modern physics. This challenge is often referred to as the cosmological constant problem, a puzzle that has continued to elude a satisfying solution. On one hand, theoretical predictions based on quantum field theory suggest that the vacuum energy should be immense, creating a cosmological constant many orders of magnitude greater than what we actually observe. In fact, the discrepancy between the theoretical and observed values is so vast that it suggests that the vacuum energy must be extraordinarily fine-tuned to yield the small yet precisely measured value that aligns with observations of the universe's expansion. So where does this mismatch come from? Why do the theoretical models of quantum field theory predict such a large cosmological constant, while reality seems to suggest something far smaller? Various potential solutions have been proposed, but none have been definitively proven. One idea is that there could be unknown physical principles or symmetries that impose constraints on the value of the cosmological constant. In this view, it is possible that additional fields or particles could interact in such a way that their contributions to the vacuum energy cancel each other out, resulting in the small value that we observe today. Other theories have taken a different approach, proposing modifications to Einstein's general theory of relativity itself, or even suggesting entirely new models of gravity. These theories might introduce mechanisms that allow the cosmological constant to evolve over time, dynamically adjusting to the changing energy content of the universe. Such ideas could explain why the value of the cosmological constant appears to be constant today, even if it was not always so. Adding another layer of complexity is the discovery of the universe's accelerated expansion, detected in the late 20th century. This finding not only highlighted the central role of the cosmological constant, but also led to the introduction of the mysterious force known as dark energy, which is thought to be driving this acceleration. While the precise relationship between the cosmological constant and dark energy remains a subject of intense debate, some researchers have suggested that the cosmological constant may not be a constant at all. Rather, it might be a dynamic quantity that evolves over cosmic time, changing in response to the evolving conditions of the universe. The quest for answers continues through ongoing efforts to probe the nature of dark energy and the cosmological constant. Missions such as the European Space Agency's Euclid satellite and the Vera C. Rubin Observatory are providing new insights into the universe's most fundamental forces. These observational surveys are designed to test our understanding of dark energy and the cosmological constant, helping to refine or even redefine our models of cosmic expansion. Ultimately, these investigations could reveal why the cosmological constant holds its specific value and may offer broader insights into the structure and future of the universe. Equally fundamental to our understanding of the cosmos are the constants of physics, such as the speed of light, the gravitational constant, and Planck's constant. These quantities are assumed to be universal, unchanged throughout the history of the universe, and central to the laws of nature. They form the bedrock of our scientific theories and have guided much of modern physics. However, questions remain about whether these constants are truly invariant. Are they constant everywhere, and have they always been so? Though we take these constants as fixed within our current framework of physics, theories in cosmology and fundamental physics have raised intriguing possibilities that challenge this assumption. Some alternative theories suggest that the fundamental constants of nature may not be truly constant across all of space and time. In particular, models involving extra dimensions or varying speed of light theories propose that these constants could have varied during the early universe, particularly during high-energy events or phase transitions. If true, this could mean that the laws of physics, as we know them, might not have always been the same, but have evolved along with the universe itself. This possibility introduces a fascinating frontier in cosmology and theoretical physics. Could it be that the constants of nature, so long considered unchanging, were once different? And if so, how might this have shaped the evolution of the cosmos? As we continue to refine our understanding of the universe's earliest moments and its ongoing expansion, these fundamental questions could lead to a deeper, more unified understanding of how the universe works. Moreover, researchers have turned their attention to distant astronomical phenomena to explore whether the constants that govern the universe might not be as constant as we once thought. Observations of quasars, supernovae, and the cosmic microwave background radiation have become crucial in this quest. These phenomena offer potential clues about how fundamental constants might evolve over time. Some studies suggest that there may be subtle, minute variations in the strength of fundamental forces, though such findings are often met with intense scrutiny and skepticism. Despite the controversies, one thing remains clear. While established theories treat the fundamental constants as unchanging, the search for a deeper understanding of the universe leaves the door open to the possibility that these constants could vary. As new experimental data and astronomical observations accumulate, scientists are refining their models to incorporate these uncertainties. The possibility that some constants may change over time introduces an exciting layer to our understanding, as researchers explore both the implications of constants remaining fixed and the potential consequences if they do not. This ongoing inquiry highlights the ever-evolving nature of scientific exploration. Our understanding of the universe is not static, it is dynamic, constantly adjusting to new evidence. Just as scientific theories change, so too might our grasp on the fundamental structure of reality itself. The universe is often described as being finely tuned, a delicate arrangement of factors that allows for the existence of complex structures such as galaxies, stars, planets, and ultimately life. Fine-tuning refers to the precise values of fundamental constants and the conditions that enable the universe to support the complexity we observe today. Even the slightest alteration in these constants could have profound effects on the universe's ability to sustain such structures. A prime example of this fine-tuning can be found in the strength of the fundamental forces of nature. These forces, the electromagnetic force, the strong nuclear force, the weak nuclear force, and gravity, are balanced in such a way that they create the conditions necessary for stable atoms to form. This stability is essential for the creation of molecules, and by extension, for the formation of more complex structures. For instance, if the strong nuclear force were even slightly weaker, atomic nuclei could not hold together, preventing the formation of atoms heavier than hydrogen. On the other hand, if the strong nuclear force were even slightly stronger, the universe would be dominated by heavier elements, leaving little room for the chemical diversity necessary to support life as we know it. Another factor contributing to the universe's fine-tuning lies in the conditions present at the moment of the Big Bang. The density of matter and energy, along with the rate of expansion, played a critical role in shaping the large-scale structure of the universe. A higher density could have caused the universe to collapse rapidly under its own gravity, while a lower density could have prevented the formation of galaxies and stars altogether. The rate at which the universe expanded was also key, and it was tuned to an extraordinary degree, allowing for a gradual cooling process that enabled matter to coalesce into the complex structures we observe today. Even the cosmological constant, a key parameter representing the energy density of space itself, plays a vital role in the universe's evolution. Its specific value is crucial in determining whether the universe will eventually collapse, remain in a steady state, or continue to expand forever. Current observations suggest that this constant is finely tuned in such a way that it permits the universe's accelerated expansion, while still allowing the formation of complex structures over time. As scientists continue to gather data, they refine our understanding of these fundamental forces and constants, further illustrating just how delicately the universe has been crafted. In this ever-expanding field of inquiry, the potential for new discoveries and insights remains boundless, keeping the mystery of the cosmos alive. In the ever-expanding realm of cosmology, one of the most intriguing ideas that has sparked deep curiosity among scientists is the anthropic principle. This principle suggests that the universe must possess the necessary properties for observers, like us, to exist. In other words, it's not surprising that we find ourselves in a universe that seems finely tuned for life. The very conditions that allow for our existence are the ones we observe. But while the anthropic principle offers one lens through which to understand the fine-tuning of the cosmos, it doesn't answer the more profound question: why do these specific constants hold the values they do? At the heart of the fine-tuning debate lies a question that resonates through the disciplines of physics, philosophy, and even astrobiology. Why do the fundamental constants of nature, those governing forces like gravity, electromagnetism, and nuclear interactions, hold the exact values they do? The astonishing precision of these constants raises one of the deepest questions in science. Is this the only possible universe, or could the constants be different, leading to entirely different physical realities? Take, for example, the electromagnetic force. If its strength were even slightly altered, the universe as we know it would look very different. Chemical bonding, which is crucial for the formation of molecules like proteins and nucleic acids, vital to life, could be severely hindered. A small change in the electromagnetic constant could make life as we know it impossible, or at the very least, radically different. Similarly, the gravitational constant plays a vital role in the formation of stars, planets, and galaxies. If gravity were weaker, it could prevent the formation of stable planetary systems, undermining the conditions necessary for life to thrive. On the other hand, a stronger gravitational force could create planets too dense, with atmospheres far too oppressive for life to exist. In either case, these alterations would challenge the notion that life, as we understand it, could flourish under such altered conditions. And yet, the question lingers. Could life arise under different physical conditions? Could other forms of life exist with a different set of constants, potentially beyond the boundaries of our universe's laws? Some theorists have speculated about this possibility, even imagining forms of life based on alternative chemistries, such as silicon-based life instead of carbon-based life. Silicon, while chemically similar to carbon, has limitations that make it far less versatile in forming complex molecular structures. Still, it remains an intriguing possibility, pushing the boundaries of what we consider to be life in a more conventional sense. What if life could exist not in the familiar form we know, but based on completely different biochemistries, perhaps relying on substances other than water as a solvent? Some researchers have hypothesized that life could take shape in environments vastly different from Earth, where life would not require water at all. This expands the very definition of life, forcing scientists to think beyond the biochemistry that has shaped our understanding of what is biologically possible. This speculation intersects with another exciting idea gaining traction in modern theoretical physics, the concept of a multiverse. According to this theory, our universe may not be the only one. Rather, there could be countless other universes, each governed by its own distinct set of physical constants. These universes might have entirely different laws of nature, and some could possess the perfect conditions for life, albeit in radically different forms than what we recognize on Earth. While the idea of a multiverse remains speculative, it opens the door to tantalizing possibilities. Could there be universes where life exists with entirely different rules? And if so, what might that life look like? Yet, as captivating as these ideas are, the notion of life in alternate universes or under different constants remains speculative at best. The true feasibility of such life is still unknown, and while it broadens our understanding of life's potential adaptability, we are left with more questions than answers. The investigation into whether life could exist under different constants or in universes governed by distinct laws continues to drive research in both cosmology and astrobiology. The answers, when they come, could revolutionize our understanding of life, the universe, and everything in it. This brings us to another profound inquiry. Do the laws of physics remain constant across the universe? Most scientists today believe that the fundamental laws of physics are uniform throughout the observable cosmos. This belief is grounded in extensive empirical evidence, with the success of the Standard Model of particle physics and general relativity offering a cohesive framework for understanding the universe. From the smallest subatomic particles to the largest galactic structures, these laws appear to hold true on all scales. However, not all theories align with this uniform view. Some cosmological models propose that the laws of physics may have been different in the early universe, particularly during the Big Bang or the phase transitions that followed. In these extreme conditions, the fundamental constants might have fluctuated, potentially leading to a different set of rules governing the universe at that time. This raises another tantalizing possibility. Could the laws of physics themselves evolve or vary, depending on the era or the environment? In this ongoing quest for understanding, scientists continue to probe the depths of these questions. As research progresses, we might uncover not only more about the universe's fine-tuning, but also the vastness of possibilities for life and the laws that shape its existence. The journey is far from over, and the answers may forever elude us, but the search itself promises to illuminate the very nature of our reality. The concept of a multiverse offers an intriguing glimpse into the nature of reality, suggesting the possibility of multiple, perhaps infinite, universes. Each of these universes could be governed by its own set of physical laws or constant, potentially varying in unimaginable ways. These different universes might look radically different from one another, giving rise to diverse forms of matter, energy, and even life itself. However, despite its allure, the idea of the multiverse remains highly speculative. It still lacks direct empirical evidence to support its existence, keeping it firmly in the realm of theoretical physics. In recent years, researchers have turned their attention to investigating the possibility of variations in fundamental constants over cosmic timescales, attempting to find clues that could lend support to the multiverse theory. One such approach involves scrutinizing the light emitted by distant quasars, by examining the fine structure constant, an essential parameter related to electromagnetic interactions. Scientists have tried to detect any possible changes. While some studies have suggested minor fluctuations, these findings have sparked heated debates and remain a subject of intense scrutiny. The results are far from conclusive, and the search for solid evidence continues. Another avenue of research explores the possibility of spatial variations in the fundamental laws of physics. Could the constants governing the universe, such as the gravitational constant or the cosmological constant, differ from one region of space to another? If true, such variations could hint at an unknown dimension of reality, one that transcends our current understanding of physics. While the dominant belief remains that the laws of physics are universal and consistent across the observable universe, scientists continue to probe the idea that certain regions of space might behave differently. These inquiries are reshaping the way we think about the universe's structure and prompting fresh lines of theoretical investigation. As our knowledge of physics evolves, these questions continue to fuel the pursuit of deeper insights into the nature of reality itself. Could we one day uncover hidden realms where the laws of physics deviate from our expectations? Or might we discover that the universe is far more uniform than we previously believed? These explorations remain at the cutting edge of science, pushing the boundaries of what we know and reshaping the way we view our place in the cosmos. Beyond the observable universe lies a vast, largely uncharted region, one that is completely inaccessible to our current observational tools. Yet, this distant expanse remains a subject of profound fascination for cosmologists and scientists alike. The observable universe, as we understand it, is defined by the region of space from which light has had enough time to reach us since the Big Bang, approximately 13.8 billion years ago. This limits our view to galaxies and cosmic phenomena that lie within a 13.8 billion light-year radius from Earth. But since the universe itself has been expanding since the Big Bang, there are vast regions beyond our observational reach. What lies in these uncharted territories? One theory suggests that beyond the observable universe is more of the same vast cosmic expanse we see within our limits, continuing indefinitely in all directions. On large scales, the universe is thought to be homogeneous and isotropic, meaning its overall structure remains roughly the same, whether we're looking at galaxies, clusters, or voids. If this theory holds true, distant regions could resemble our observable universe, containing stars, galaxies, and structures similar to those we already know, extending far beyond the limits of our sight. Another possibility is the idea of a flat or infinite universe. If the universe is infinite, the space beyond what we can observe would stretch on forever, continuing without end in every direction. In this scenario, distant regions would likely harbor structures similar to those we've observed: stars, galaxies, and clusters, repeating in an endless cosmic expanse. The sheer vastness of this infinite universe challenges our ability to comprehend its scale. Alternatively, the multiverse theory offers a radically different vision for what exists beyond our cosmic horizon. Instead of simply more of the same, it suggests that our universe may be just one of many, each potentially governed by distinct physical laws or constants. In this framework, separate universes or pocket universes could exist, each with its own unique properties. These universes might feature entirely different dimensions, forces, and even fundamental constants, making them vastly different from our own. The potential diversity of these universes opens the door to even more extraordinary possibilities, where different forms of matter, energy, and perhaps even life could emerge, shaped by entirely alien rules of physics. While the multiverse theory is still in its infancy and lacks definitive proof, it presents an exciting, if speculative, frontier in cosmology. Each new discovery in physics brings us one step closer to understanding the true scope of reality and the possibility that our universe is just one of many, existing within a vast and diverse cosmic tapestry. Moreover, the very fabric of space-time may conceal mysteries far beyond the observable universe, hidden in realms that challenge even the most sophisticated theories. Hypothetical concepts, such as string theory, suggest the existence of additional dimensions, far beyond the familiar three-dimensional space and one-dimensional time. These dimensions, though not directly observable, hint that reality itself might be far more complex and expansive than we can currently comprehend. Ultimately, while we cannot yet peer beyond the limits of the observable universe, theoretical explorations continue to fuel our understanding of the cosmos. These ideas serve as a profound reminder that the universe is not only vast, but also teeming with potential possibilities, awaiting discovery. They invite scientists into an ever-deepening inquiry about the nature of existence, urging them to consider what mysteries may still lie in wait, just beyond the reach of our current knowledge. One of the most intriguing challenges in modern astrophysics is the quest to observe the universe's first stars, often referred to as population 3 stars. These ancient celestial bodies are believed to have formed from the primordial gas, primarily composed of hydrogen and helium, that existed shortly after the Big Bang, approximately 100 million to 400 million years after the event. What makes these stars particularly fascinating is their composition. They were likely massive, short-lived, and almost entirely made up of the very first elements created in the universe. Studying these stars holds immense potential for unveiling crucial insights into the early universe, shedding light on the processes that led to the formation of galaxies and more complex structures. However, observing these ancient stars directly presents significant challenges. One of the main hurdles is their extreme distance from Earth. Many of them reside at redshifts beyond 6, meaning that the light we would need to detect them has been traveling for billions of years. As a result, this light is faint and dimmer compared to the brighter stars we observe today, making their detection incredibly difficult with current telescopic technology. Despite these challenges, the pursuit of understanding these first stars continues, as they hold the key to unlocking deeper truths about our universe's origins and its earliest stages of evolution. However, advancements in technology and observational techniques offer hope for the future. The next-generation space telescopes, such as the James Space Telescope, JWST, set to launch in the coming years, are engineered to observe the universe in infrared wavelengths of light. These wavelengths have a unique capability. They can penetrate the thick clouds of dust and gas that often obscure observations in optical ranges. As these advanced instruments come online, they hold the potential to detect the faint signatures of the first stars or the ionizing radiation from their formation, both of which played a pivotal role in the reionization of the universe. Beyond direct observations, astronomers are exploring innovative, indirect methods to study these early cosmic phenomena. One of the primary strategies is examining the cosmic microwave background, CMB radiation, which offers a glimpse into the conditions of the early universe. By analyzing the fluctuations in temperature and the polarization patterns of the CMB, scientists can infer vital information about the universe's early stages, offering clues that could eventually unlock the mysteries of the first stars. Additionally, simulations and models mimicking the formation and behavior of population 3 stars, considered the first generation of stars, can provide valuable insights into their characteristics and their role in shaping the universe. While the task of directly observing the universe's first stars remains daunting, ongoing technological advancements and novel observational strategies are making this goal seem within reach. The potential discovery of these primordial stars would be a monumental step forward in understanding the early universe, shedding light on the processes that led to the formation of galaxies, stars, and the complex cosmic tapestry that we observe today. Probing the universe's so-called dark ages is crucial for understanding cosmic history, particularly the period after the Big Bang. This was the era when the universe expanded and cooled, but before the first stars had formed, spanning roughly from 400,000 years to about 1 billion years after the Big Bang. The Dark Ages are so named because, during this time, the universe lacked bright sources of light, making it a challenging period to study using traditional observation methods. One of the most powerful tools for investigating this elusive epoch is the study of the cosmic microwave background, CMB radiation. The CMB is the afterglow of the Big Bang, radiation released when the universe cooled sufficiently for electrons and protons to combine and form neutral hydrogen atoms. This event allowed photons to travel unimpeded through space, offering a snapshot of the universe when it was about 300,000 years old. By analyzing the temperature fluctuations and polarization patterns within the CMB, scientists can gain insights into the conditions of the early universe, setting the stage for understanding the subsequent Dark Ages. Another vital method of probing the Dark Ages involves the exploration of high redshift astronomical objects. The light from these distant galaxies and quasars takes billions of years to reach Earth, essentially allowing astronomers to peer back in time. By studying objects with redshifts greater than 6, scientists can make inferences about the universe during the Dark Ages. The light emitted by the first stars and galaxies offers clues about when the first luminous sources emerged and how they influence their environments. A particularly promising target for this kind of research is the detection of population 3 stars, the first generation of stars believed to have formed from primordial gas, primarily composed of hydrogen and helium. Understanding the formation and impact of these stars will offer essential insights into the reionization epoch, a critical period when the universe transitioned from the dark ages into an ionized state filled with light. Upcoming observatories like the James Webb Space Telescope are designed to probe this pivotal era by observing infrared wavelengths that could provide critical information about early stars and galaxies. Another technique gaining attention is the search for signatures left in the intergalactic medium during the Dark Ages, particularly through a process known as 21-centimeter hydrogen mapping. This method capitalizes on the hyperfine transition of neutral hydrogen, which emits radiation at a frequency of 21 centimeters. By mapping variations in this signal on large scales, astronomers can infer the density and temperature of hydrogen gas during the Dark Ages, revealing details about cosmic structure and the conditions that ultimately led to the formation of the first galaxies. The combination of these observational and theoretical approaches is steadily building a more comprehensive understanding of the Dark Ages. As technology advances and new observational tools come into play, scientists continue to refine their models and expand our knowledge of this enigmatic period in cosmic history. Ultimately, these efforts are poised to unravel some of the deepest mysteries of the universe, providing insights that will reshape our understanding of the cosmos. Probing the universe's dark ages is a journey that promises to illuminate the most fundamental aspects of cosmic evolution and formation. However, the ultimate limits of what we can observe in the universe are not merely defined by the power of our telescopes or the sophistication of our technologies. They are intricately tied to a combination of physical, technical, and philosophical factors. As we venture deeper into the cosmos, it becomes clear that understanding these limitations is as crucial as our ambition to overcome them. At the heart of these limitations is the immutable speed of light. Since light travels at a finite speed, every astronomical observation is, in essence, a glimpse into the past. The farther an object is from us, the longer its light takes to reach Earth. As a result, we are always looking at events that occurred billions of years ago. The farthest visible objects are those whose light has traveled for such long periods that they have crossed the vast expanses of space to reach us, spanning distances so immense that we encounter an effective boundary, the observable universe. This boundary is defined by what we can detect, and beyond it lies the cosmic horizon, about 46 billion light-years away today. Any light originating from regions beyond this limit has simply not had enough time to reach us since the Big Bang. But the universe doesn't just limit our view through time, it also complicates it with its ever-expanding nature. As distant galaxies recede from us due to the expansion of space itself, their light is stretched toward longer, redder wavelengths. This phenomenon, known as redshift, can push their light into ranges that are no longer detectable by our current instruments. Some galaxies may be so redshifted that they become invisible, forever eluding our grasp. Furthermore, the farther away an object is, the fainter it becomes, making it increasingly difficult to distinguish from the cosmic background noise, which masks our ability to observe these faint signals. In addition to the vast distances, the challenges of technological constraints play a pivotal role. The sensitivity, resolution, and dynamic range of our telescopes and detectors ultimately define the limits of our observations. Current technology, while impressive, has its limits, such as the size of the mirrors that gather light or the precision of the detectors that capture it. These constraints hinder our ability to observe particularly faint or closely spaced objects, limiting our capacity to explore the distant reaches of the universe. Ground-based observations come with their own set of challenges. The Earth's atmosphere, while vital for life, interferes with the clarity of astronomical observations. The atmosphere absorbs and scatters specific wavelengths of light, especially in the ultraviolet and infrared regions, leading to image distortion and loss of clarity. While space-based observatories and advancements in adaptive optics have mitigated some of these effects, the need for robust, resilient instruments capable of functioning in the harsh conditions of space remains a major hurdle. Space-based observations, despite their advantages, are not without their own set of challenges. The instruments required to operate in space must be highly specialized and built to withstand extreme conditions. Furthermore, their maintenance and repair are difficult, if not impossible, once in orbit. On a more philosophical level, the concept of observational limits raises profound questions about the nature of reality itself. The notion of the cosmic horizon, coupled with ideas like cosmic inflation or the potential existence of multiverses, suggests that there may be regions of the universe that are forever beyond our observational reach. Can we truly know everything about the cosmos, or are there parts of it influenced by phenomena we cannot detect that will remain hidden from us forever? For instance, areas affected by cosmic inflation, or even entire universes with different physical laws, may remain completely inaccessible no matter how advanced our technology becomes. As we continue to develop new technologies and refine our observational strategies, we will undoubtedly push these boundaries further. However, certain fundamental laws like the speed of light, the expansion of the universe, and the natural constraints of our environment will always define the ultimate limits of our observations. These laws, while limiting in some respects, also serve as the foundation of our understanding of the cosmos, offering a framework within which we continue our quest to uncover its deepest secrets. One area that highlights both the challenges and the promise of modern astrophysics is the detection of gravitational waves from the early universe. These ripples in space-time, predicted by Einstein's general theory of relativity, are generated by the acceleration of massive objects, such as merging black holes or neutron stars. Gravitational waves hold the potential to revolutionize our understanding of cosmology, providing insights into the birth of the universe itself and the fundamental forces that govern its evolution. Yet detecting these elusive signals is a monumental challenge, demanding innovations in both technology and observational strategy. In the end, while the boundaries of what we can observe may be determined by the interplay of physical, technical, and philosophical factors, the pursuit of knowledge continues. The universe, in all its vastness and mystery, remains an uncharted frontier, a frontier we will continue to probe, explore, and perhaps one day fully understand. In the earliest moments of the universe, during events like the Big Bang, cosmic inflation, and various phase transitions, gravitational waves, ripples in the fabric of space-time itself, were born. These waves were unlike anything we can experience today, arising from the extreme conditions of the universe's infancy. One of the most ambitious quests in modern astrophysics is to detect these elusive gravitational waves, specifically those generated during this formative period. Scientists aim to observe the cosmic background gravitational radiation, a faint signal created by these early waves. In theory, the rapid expansion of the universe known as cosmic inflation, which occurred just after the Big Bang, would have left behind a unique stochastic background of gravitational waves. If these waves contain traces of the minute fluctuations that occurred during inflation, detecting them could offer a groundbreaking look at the early universe's dynamics, providing insights into its birth, growth, and evolution. To accomplish this monumental task, researchers use large-scale observatories with extraordinary sensitivity. Current ground-based detectors, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, and the Virgo collaboration, have proven their worth by detecting gravitational waves produced by astronomical events such as binary black hole mergers. However, these detectors are most attuned to higher frequency waves, typically above 10 Hz, which limits their ability to capture the low-frequency gravitational waves that were generated in the early universe. In response to this challenge, scientists are looking toward the stars, literally. Advanced space-based observatories designed to detect these low-frequency gravitational waves are in development. One of the most exciting projects is the Laser Interferometer Space Antenna, LISA, a mission that aims to detect gravitational waves in the frequency range below 1 MHz, extending up to about 1 Hz. By employing a constellation of spacecraft separated by millions of kilometers, LISA will be able to detect the tiny variations in distance caused by passing gravitational waves. This unique capability makes it an ideal tool for unveiling the faint, low-frequency signals from the early universe, possibly revealing its hidden secrets. Another promising method to detect these ancient waves lies in the study of the cosmic microwave background, CMB, the faint afterglow radiation left over from the Big Bang. Specifically, researchers are focusing on its polarization patterns, which could be altered by the inflationary gravitational waves. These waves would leave behind a distinctive signature known as B-mode polarization in the CMB. Projects such as the BICEP and Planck missions have already made significant strides in mapping the CMB, and future missions like the Simons Observatory aim to explore these polarization patterns further. Detecting B-modes would provide a powerful tool for studying the earliest moments of the universe, offering clues to the very origins of space, time, and matter. Despite the immense progress made so far, the detection of gravitational waves from the early universe remains a work in progress. However, with the rapid advancement of technology and the development of specialized observatories, we are on the verge of uncovering some of the most profound cosmic events that shape the foundation of our existence. These gravitational waves hold the promise of revealing the conditions of the early cosmos, giving us a clearer understanding of phenomena such as cosmic inflation, phase transitions, and the fundamental nature of space-time itself. Yet, even as we inch closer to these revelations, we must acknowledge that we've only scratched the surface of what we truly don't understand about the universe. There are mysteries still beyond our grasp: dark matter, quantum entanglement, the nature of time itself. These aren't merely intellectual puzzles. They are gaps in our fundamental understanding of reality. For every question we've begun to answer, countless others may lie hidden, waiting for future generations to unearth. In the end, science is not just about finding answers. It's about relentlessly expanding the boundaries of what we can question. The theories that seem cutting-edge today may appear quaint to future physicists, just as geocentrism seems outdated to us now. So, what's next in the search for the universe's deepest truths? What paradigm-shifting discoveries await on the horizon? And what assumptions are we making now that future generations will one day overturn? Only time will tell.